Okay, so I think we can start our second session, this second day of conference, and our first speaker is Gia Dvali from LMU. So please, Gia, the floor is
yours. Thank you very much. I would like to thank organizers for the invitation. It's a pleasure to be here to give this talk. So yeah, my talk is about black holes and saturons, yeah, it's based on a series of papers. The main paper is probably this one, where the concept was very well defined, and also bunch of papers with my collaborators. Yeah. Actually, the one specific I will single out the paper with Dr. Satelashvili. Okay, so black holes, as we know very well, they are beautiful, and also they are considered to be mysterious because of several properties of their time evolution and the way they time evolve and the way they process information or store. And these are well-defined, well-understood properties of black holes. So it's, for example, they are classically stable and eternal. Quantum mechanically, they decay with approximately thermal spectrum. They carry entropy, which usually is considered to be mysterious, a strange form, because it's area in units of Newton's constant. Of course, I'm ignoring here a factor of 4 and etc. And also, you have this object that carries huge entropy, so huge microstate degeneracy, and which means that it stores huge information, actually maximal information, and it decays, but at the same time it doesn't emit information at the beginning. So there is a minimal time scale that we have to wait before we start even resolving this information. And so this so-called pages time, which is proportional to volume or entropy, depending how you want to write it. Now, okay, so for several years I started this project sort of to try to demystify black holes in the following sense, that what I'm trying to prove is that these properties of black holes, they are not originating from gravity or quantum gravity, but they are common. They're common to objects that are called saturons, and these are the objects that saturate certain bound, which are maximal microstate degeneracy, maximal entropy. So, which in a unitary theory. So, okay, and so basically, black holes are one representative of this huge class of objects. It's just we never look for that. And so basically, the question that I was trying to ask is how special are black holes as compared to other objects? And this question actually was never posed before in the literature. And probably the reason is that it looks ridiculous. Of course, we understand that black holes are special. For example, if you take, I don't know, whatever object, let's say Apple, and want to compare it to a black hole of the same mass or same size, obviously Apple and black hole are very different. Pair objects, we have to bring them to the same universality class. And the universality class for black holes was never defined. Can you hear me? Because can you hear me? Can you hear me?
Yes, we hear you. Yeah.
Yeah, because somehow it told me that there was something with the internet. Okay, thanks. So therefore, we have to bring these objects into the same universality class. Okay, so now what is the universality class for black holes? And here is my definition of that. So what I'm trying to say, what I'm proposing is that there is an universal bound on entropy, and the bound is the following: on microstate degeneracy, that as an object can attain in any unitary theory, well-defined theory. So if you have an object that of certain size R, of self-sustained object, of course it has to be self-sustained, the maximal entropy, microstate entropy, is bounded by the area of the object, divided by the Goldstone coupling. So G gold stands for Goldstone coupling. Area, of course, scales as radius of the object times d minus 2. So d is the number of space-time dimensions. And this quantity is well defined in arbitrary number of dimensions. Even in 2 dimensions, it's well defined. It's a number. G is the Goldstone coupling. Okay. Now, the Goldstone coupling you can trade, as we know very well, for Goldstone decay constant, so-called Goldstone scale. It's simply a square of that inverse square. And so correspondingly, you can also define dimensionless quantum coupling of Goldstone. If you have a process, let's say some scattering process with momentum transfer, let's say given by some scale, some de Broglie value, 1 over r, then the Goldstone coupling actually is inversely proportional to the area of r. This was somehow also never noticed. I've never seen in the literature this being noticed and pointed out. So Goldstone coupling actually scales like inverse area. All right, so therefore we can rewrite. This doesn't introduce any new definition. This is just well defined. If you have for every Goldstone, this coupling is uniquely defined. So you don't have to reinvent everything, but you can rewrite also entropy, therefore, in terms of dimensionless coupling. So inverse of dimensionless coupling. Okay, so therefore, this is the maximal entropy any object can have. Now, where are the Goldstones coming from? You can ask this question. Why is this universal? And that's precisely what makes this mount universal, because Goldstones are always present. You cannot have an object which has microstate degeneracy, large microstate degeneracy, without Goldstones. Why? Because any self-sustained object breaks spontaneously Poincare symmetry. At least Poincare symmetry. Usually there are other Goldstones, as we'll see, but at least it always breaks Poincare symmetry. And so G Goldstone of Poincare is unambiguously defined, always. If you give me an object, I can always tell you what Goldstone Poincare is. That's why it's a very useful characteristic, because it's independent of gravity. Yeah. Now, in general, for example, if you give me a bound state of n quanta of some wavelength r, so let's say self-sustained bound state of weakly interacting quanta, or a wave packet, then you can see easily derive that Goldstone coupling is 1 over n times the area. Okay. Now, the states of high entropy, they contain other Goldstones, as we'll see, but Poincare is universal, and therefore it's useful to formulate the bound in the language of Poincare Goldstone. And so therefore, the maximal entropy objects, therefore, have this entropy, and they are called saturons. They saturate the entropy bound. Compatible with unitarity of the theory. Now, in this talk, I'm not going to give you many arguments. These arguments are given in the papers. It's very interesting how theory maintains this bound, how theory makes sure that you can never violate this bound. It's really fascinating to see how it responds in different cases. But there are certain universal responses. For example, one is that there is a correlation between, if you have a state that's a macro state that saturates the entropy bound, there's a correlation, one-to-one correspondence between the saturating scattering amplitudes by the same object. So, for example, if you have 2 to n, so with the occupation number given by the again inverse coupling. So this is usual. These are the usually saturated states. I see a hand, but I was told to answer questions towards the end. So
yeah, we can postpone.
So that's yeah. Please come. Yeah, I will. Yeah, make sure that it's fully answered. Okay, then. And then, if you evaluate this scattering amplitude, you can see that actually scaling at large n is given by this formula of cross section, and then you see immediately one way to see why there is this bound in the theory. Okay, so there are of course there are other signatures and other arguments. Now there is also an universal connection between the timescale of information retrieval from this state that you have which is also expressed in terms of this coupling of Goldstone. So it's basically R divided by the coupling alpha, this dimensionless coupling. Or you can rewrite it because of for saturated states, you can rewrite it as proportional to the entropy or volume. So very, very similar to Page's bound, actually identical to Page's climb. This is again universal. So now it turns out that once you have this Saturon states, they have virtually all the properties of black holes. Actually, I don't know any exception. So they have, of course, they have area low entropy. They have they evaporate thermally, very similar to Hawking time evaporation. Semi-classical, they have information horizon. The time of information retrieval is very similar to Page's time. They saturate scattering amplitudes like black holes, also like black holes saturate scattering amplitudes, and so on. So we can run a quick check on a black hole, because for black hole, Goldstone is a graviton. So obviously, black hole breaks Poincare invariance. Actually, there is nothing obvious about it because again, this was never noticed. That it was never discussed in these terms. But if you think once you think from Saturons and you want to make connection with a black hole, we can see that black holes break Poincare symmetry, and the corresponding Goldstone decay constant is given by the Planck mass. And so therefore the entropy of a black hole is area, but not necessarily area not in, of course it's area in the Planck units, but the meaning of Planck is that for a black hole, Planck is also a Goldstone coupling. And this is new, and this is absolutely crucial for defining the universality class for black holes. And of course, from there, everything follows. You can see that all the properties of black holes are like properties of Saturons. Okay, so therefore, there is black hole Saturon correspondence in terms of parameter, all the parameters of the theory. Now the connection is not between theories. You know, this is that's why it's so beautiful, because it's a connection between very specific states in very different theories, but saturated states. Okay. So now usually what I do, I mean, these concepts are of course very new, and so they are new, and quite some progress has been made. And usually what I'm trying to do, I try to bring one example per talk. So I change examples when I go from one talk to the other. And for this talk, I decided to give this example that we worked out, Otari Safelashvili and me. This is in Gross-Nivea model. Okay. Now the reason I brought this model, because it's very informative, because this is the model that is naively this is a theory that naively it's complete opposite of gravity. Okay. First, it's two-dimensional, this theory. Secondly, this theory is asymptotically free, so it's it's a UV complete theory, and calculable. So we know essentially everything about this theory. Now, people that are interested in large N physics and large N QCD, in that community, this theory is very well known as a sort of prototype for certain features of QCD, for example, asymptotic freedom. So what is this theory? This is a two-dimensional theory of fermions. So there are 2n Majorana fermions. You can of course, as usual, you can write fermions in Majorana basis or in Dirac basis. And there is a flavor group. There is an SO2n flavor group of fermions. And so the theory, as I said, is asymptotically free. Now, I denoted deliberately the interaction by the same symbol alpha, because for the saturated state, this alpha is also equal to the Goldstone coupling. So therefore, in order not to introduce many different notations. I just denote it right away by alpha. Now, this model is, as I said, is extremely well understood, and it's asymptotically free, and it has spectrum of bound states. And the spectrum of bound states is also very well understood. Also, the S matrix is very well understood. So in large n, this is exact, and so there are bound states of n fermions. Little n is occupation number of fermions. Okay, and so there is a relation between the n and the mass of the bound states. Now, each bound state transforms as an antisymmetric tensor of SO to n group, and the generates therefore directly follows from group theory. So the number of states is given by this binomial coefficient, number of microstates. And so therefore each bound state, it's a macroscopic object. So, and it's highly degenerate. Okay, so it has entropy. So here comes the new part now. Now we are, this spectrum is known, but now our novelty here is to show that these are saturons and to make connection to show that these behave literally like black holes. Now the bound state of maximal degeneracy has mass given by this formula, okay? And the size is given by the Compton wavelength of the fermion. And so in this theory, there is a dimensional transmutation and generation of the mass and so on. And so the entropy, as you can see very easily, you can use the Stirling formula, and so it scales like n. Okay, so it's of order n. Now the theory saturates unitarity bound for n being 1 over alpha. So n cannot exceed 1 over alpha. What does it mean, saturates unitarity bound? It means that the theory changes the regime, and the way to understand this regime change is precisely this formation of the bound state. Okay. Now the reason is that the collective coupling n times alpha in this theory runs, and correspondingly, it generates the mass gap, and the running stops at precisely at alpha n order 1. So that's the point. Now, so now this state, that maximal degeneracy state, is a saturon. Okay. The entropy saturates exactly that bound that I gave, and also this is correlated with the saturation of the cross section. Okay, by this object, and here is very nice because we can evaluate cross section. Okay, and you can see that indeed. This reproduces typical scaling that I gave. Okay. Now, by the way, this is very similar to the scaling that we got. So in general, this is typical for the scaling on 2 to n amplitudes near the saturation point. In particular, to 2 to n graviton amplitudes. Okay, which we have computed, our group and also a group by Adalzi, Bianchi, and Veneziano. So it was computed in directly, both in quantum gravity, also in string theory. So this is a computation that is pretty well understood. And this 2 to n scattering within the black hole M portrait, okay, in which black hole is considered a saturated state of n gravitons, has scaling in which it shows why black holes saturate scattering amplitudes. Okay, and so we are observing very similar behavior in this 1 + 1 dimensional model, which has nothing to do with gravity. Okay. Now at the saturation point, you can see very easily that there is a complete correspondence between the entropy of the bound state and the Bekenstein-Hawking formula, because precisely the Goldstone coupling is the dictionary between the two. Now, as I said, the quantity area is well defined in D = 2, and G Goldstone is also well defined. And as you can see, so area is a number order 1, and G Goldstone is a coupling of the Goldstone. So it's exactly the same relation as for a black hole. Now, what about Hawking evaporation? Again, this bound state, once you couple it to a pion, okay, a massless pion, of course it decays, and the coupling with pion is again well defined. It's given by the pion decay constant, fermion mass pion decay constant. Now, pions, of course, they form representation of the flavor group, obviously, because theory has flavor symmetry, just like in QCD. They form this flavor representation. And so the saturon starts emitting pions. This fermion bound state in Gros-Nivier starts emitting pions and decays. Okay, with the rate, which is Hawking rate. So at large n, okay, in semi-classical limit, it reproduces Hawking rate. So here, this typical. Now, of course, the great advantage here is that we can. We know how to compute this in full quantum theory. And now we understand what this operation is, where this operation is coming from. It comes from the scattering of constituent fermions into pions, and so this reproduces the thermal rate of Hawking. Now, this is very so. In other words, if you are an observer that has no idea, so you're observing this object, this saturon in Gros-Nivier, and you see that it emits as if it's a thermal state. Of course, it's not a thermal state. But to distinguish it from the thermal state, it's a pure state. But to distinguish it from the thermal state, it takes time because you have to gather a lot of evidence. And in double scaling limit, in semi-classical limit, that time scale goes to infinity. So in semi-classical limit, in which it is large n limit, okay, infinite n limit. So it's the spectrum, you cannot distinguish it from thermal. And you think that it's a thermal spectrum, but it's not. So only in that limit it sort of merges with thermal spectrum because you cannot resolve it. Now, of course, so here's the point, right? So what's the difference between thermality and, well, the difference is 1 over n. These are 1 over n corrections. So the 1 over n corrections are 1 over n. So if you are an observer and you do measurements with the precision of 1 over n, then you will purify the state. You will see that it's a pure state. Okay. Now, information is also hidden in 1 over n corrections. And here, why this model is nice, because this is the simplest model in which you can really fully trace quantum information from the beginning to the end. Okay, so I can encode quantum information in the initial state of saturon, okay, without any ambiguity. So, and then you should try to recover this state. Okay, so the initial state by measuring decay products. And of course, the information is encoded in the flavor state of the saturon. And so this information is carried away by the quantum numbers of pions. Now you can ask, okay, how long does it take for Alice, an observer, an external observer, to start decoding information stored in this initial state? And you can derive it. It's exactly like Page's time. Okay, exactly the same relation. So what you are observing is that there is nothing mysterious about the fact that you have to wait, which is also, by the way, half decay time of this object. So you have to wait until half decay time of this object in order to start recovering, not to recover, but start readout of the information. So this is a generic property of saturated systems. This is not a specific property of gravity. Again. Now, so what I want to say is that what we are observing that there is this black hole saturon correspondence. It is independent of the dimensionality. It is independent of anything, essentially. So, in other words, no matter how different your theories from gravity, or your theories are, once you reach the saturated state, that saturates the bound of the entropy that I gave you. By the way, as a byproduct, this bound state in Gros-Nivier also saturates so-called Bekenstein bound on entropy. Okay. The problem with Bekenstein bound is that Bekenstein bound is not formulated in terms of unitarity or coupling. So therefore, it's not, because you can have, I gave examples, you can have bound states in which, for example, Bekenstein bound is fine, but they violate this bound, and such theories are inconsistent because they cannot be unitary. So, but sometimes it happens that the two bounds. So in other words, the bound that I gave is more stringent, but sometimes it happens that they are saturated simultaneously. So, for example, this is what happens for these bound states. So the correspondence between the different theories is formulated in terms of what I call trans-theoretic parameters, because trans-theoretic, the Goldstone decay constant, okay, represents a trans-theoretic parameter. You can define it in arbitrary theory, Goldstone of Poincare symmetry. That's why it's very useful. Okay, so this is sort of a summary of what we are observing. Now, by the way, the list of these examples that we have is very long. Okay, unfortunately, I cannot discuss all of those in one talk, and but all of them are very interesting. For example, one example that I found especially interesting is what happens in large N QCD when the gluon state approaches saturation. So what emerges is the way theory prevents this entropy from entropy bound, this Goldstone bound on entropy from being violated, is by confining theory, by generating mass gap and confining the theory. Similar to this in this example of Gros-Nivier, right? Gros-Nivier is the same thing, because what happens is that the alpha times n runs, and so entropy of the bound state is set by alpha times n. If you could make alpha times n the collective coupling, so-called Toft coupling, arbitrarily large, you would violate the bound. But that's not possible, because when Toft coupling hits order 1, you have dimensional transmutation, and theory generates a mass gap. So in large N QCD, it looks like confinement is the mechanism for preventing that. And so that's very interesting. So the confinement can be understood as a counterpart of black hole formation, and so yeah, so that's one thing. Even in ordinary QCD, again, unfortunately, I don't have time to discuss that, but Raju Vanagopalan and myself, we wrote a paper some time ago pointing out that in ordinary QCD, there is a state, so-called color glass condensate, and it looks like that state shares, it's a saturated, it looks like it's a saturated state in this sense, and not only in terms of occupation number, but in terms of this entropy. And it shares all these properties with black holes. So it's very interesting. So now, of course, this fact also gives us the fact that now we can have, so you see how the logic goes, right? So what I'm saying is that black holes are not special. They are black hole property. Of course, black holes are special, obviously, but gravity is to gravity. But black holes belong to a certain universality class of saturons, of saturated objects. And now, looking at saturated objects, we see that they reproduce all the known properties of black holes, but we also understand why they do that. And so this is very important, because this gives information about how the black holes work. Okay. For example, Saturns make it very clear that black hole evaporation cannot be thermal, because Saturn evaporation is never exactly thermal. There are always 1/s corrections that break thermality, obviously. Also, the ordinary assumption about black hole evaporation is that it is self-similar. So in other words, when black hole emits some quantum, it shrinks and becomes a smaller black hole. You would be surprised to notice that this is not supported by any computation. It's literally an extrapolation of the computation which was done in no back reaction limit. So Hawking computation, of course, is exact, but it's done in no back reaction limit. And so what saturons tell us that most likely that's not the case. So when black hole emits quantum, it doesn't become a carbon copy of a smaller black hole. It's not even obvious that black hole shrinks in size when it emits quantum. So all these things are very important to take into account in understanding black hole physics. And let me finally conclude a couple of concluding remarks. Actually, I'm ahead of time. That's good. So now all the saturated objects that we know, explicit examples of saturated objects, they represent, so they could be solitons, instantons, other bound states in the theories, Q-balls, and so on. They all represent saturated states of quanta. For example, in Gross-Nivier, they represent bound state of fermions, saturated bound states of fermions. And so this hints very strongly that black holes do represent saturated states of gravitons. I mean, this was exactly the idea proposed by my collaborator Cesar Gomez and myself long ago. And so now the saturation gives it an independent support, because I never assumed in this talk anything about constituency of a black hole, but black hole import rate, our idea is that black hole is a saturated state of gravitons, so this is what saturated states are in other theories, and they do reproduce properties of black holes. So this is a pretty strong indication that we are on a right track when we say that black holes are composite and they are bound state of quanta. Okay, so yeah, I think I can just simply stop here. Yeah, so maybe just as a side remark, also, as I said, in this import rate, I already mentioned that the black hole creation, black hole formation in high energy scattering, for example, we know, so from semi-classical arguments, there's a long time there was understanding of this by Toft, Veneziano, Amati, Ciafaloni, Gross, Mendel, and others. So there are arguments that if you have very high energy collisions, so let's say 2 quanta, all right, you form a black hole. In other words, somehow the cross section has to be dominated by a black hole. But in order to understand this microscopically, you need some kind of microscopic guideline, which was not there before. And what quantum import rate and what saturation independently, so these two ideas completely independently, they tell us that black holes are saturated states. This means that if I form a black hole in two particle collision, this is a process of saturation, right? Because in two initial state has very little microstate entropy, microstate degeneracy, and final state has huge degeneracy, and with gapless modes, etc., and so on. And how that happens, the process that describes that at the level of S matrix quantum field theory is 2-to-n scattering process. And as I said, this has been computed, and very interestingly, this precisely indeed gives us the saturation of cross section. So this also gives a pretty strong supporting argument that we are on the right track when we say the black holes are large N states, composites of many gravitons. Okay, so let me finish here, and thank you very much. And if there are any questions, of course, I'll be happy to answer. Actually, Luca had a question, I see.
So there is a question from Luca, who is here. Just let me maybe do this. Just 1 second. Okay, Luca, please, you can ask the question.
Can you hear me?
Yeah.
Yeah, okay. First of all, very nice, inspiring talk. I wanted to do some common question. So, regarding in particular when you mentioned the Goldstone boson from the spontaneous breaking of Poincare symmetry. Actually, it's well known that Goldstone theorem it's quite problematic when you talk about space-time symmetries. In particular, first of all, because one of the assumptions of the Goldstone theorem is the translation invariance of the vacuum. So in principle, you cannot even apply Goldstone theorem, but clearly, in many cases, I'm not saying there are not. For example, in crystals, you have phonons, acoustic phonons, which are Goldstone bosons for the broken translation invariance. But for sure, there are various results which say that at least there are problems with countings of Goldstone bosons when they exist, or if they exist, translational Goldstone boson, sometimes they don't exist Goldstone boson due to rotation and so on. That's a first comment. And second one is that even when you have spontaneous breaking of space-time symmetry, in this case, due to the existence of an extended object, it's not said that these would be Goldstone boson are a dynamical object. For example, you can take the work by the group of Mezzawa and Alberta, for example. There's a very nice paper by Matsumoto, Semenov, and Mezzawa about this, and they show that when in quantum field theory, when an extended object is created by boson condensation, in that case of a breaking of internal symmetry, then in that case you have some will be Goldstone boson, but are not dynamical objects, and their creation and annihilation operators can be combined in order to define quantum coordinates, quantum mechanical coordinates of a system, because they bring zero momentum. So you have, in that case, some kind of Goldstone, but are not dynamical objects, and so they cannot be used as you would like in this case. So I wanted to ask you some comments about this. So Goldstone theorem validity.
Yeah, sure. So yeah, I get the point, and I'm happy to answer. So okay, first of all, we studied these Goldstone bosons of broken space-time symmetries with Misha Schiffman and myself at least as early as beginning of 90s. For example, there, in case of solitons, when you have extended solitons in supersymmetric theories, especially in BPS case, there is an unambiguous interpretation of the moduli space in terms of Goldstone modes. And so now the typical mistake that people make often when discussing these Goldstone theorems and stuff. Also, yeah, before I do, also when we talk about breaking of Poincare symmetry, sure, yeah, we know that they're well-known, not problems, but they're well-known differences in counting the Goldstone bosons, and that the reason for that is totally trivial. The Poincare group is not a direct product of translations and Lorentz boosts. So therefore, for example, there is no way to break translation symmetry without also breaking Lorentz boosts. These are well-known things, and so in each particular case, there is unambiguously there is a gapless mode. This is unambiguous. So when I'm talking, so when you say dynamical, non-dynamical, I don't understand what you mean, because the having Goldstone excitation when you break Poincare symmetry by a bound state is well defined, has a very well defined meaning. Meaning is that there is a mode, there is an excitation. If I write Hamiltonian on that state, there is an oscillator that becomes gapless in large n limit. Okay, so when n goes to infinity, this oscillator becomes gapless, and there is existence of this gapless mode is in one-to-one correspondence with the breaking of corresponding generators of Poincare symmetry. So in each case, this counting is unambiguous. Now, so there is absolutely no ambiguity there. Also, and of course, this object is dynamical. I mean, whenever you have an oscillator with certain gap, there is a certain price you have to pay to excite this oscillator. And this unambiguously defines what I call Goldstone coupling. So in other words, what I want to say is that all the statements that I'm making here are not out of blue, that I'm just simply imagining that because there is a breaking of Poincare symmetry, there must be these are very well-defined objects for each particular Saturn. You can check example by example. In each particular example, these Goldstone modes are unambiguously defined. So they're fully consistent. And yeah, I mean, of course, we know that there is a difference in counting whenever the group is not a direct product. That's obvious because because some of the generators are linked, and for case of Lorentz Poincare, this is because of the connection. So yeah, absolutely. So all this is perfectly fine, and it's perfectly taken into account. Yeah. So I don't know if there was anything else in your question. But this, of course, this is an important comment. Thanks for making this comment. Yes.
Yeah, thanks. What I meant by dynamical is that I don't know if you know these works, but I was studying by Omezawa and collaborators, where this extensively studied tons of papers, formation of extended objects in quantum field theory by means of boson condensation. And in that case, they prove that they should you should have some bound state described by zero momentum modes.
So again, as I'm saying, so we can go into technicalities. There is absolutely, I would be happy to do that. But what I'm saying is that there is no ambiguity that whenever you have an object, and any object, you simply cannot have something that you call an object, either soliton or whatever, that is not breaking at least part of Poincare invariance spontaneously. And there is unambiguously an oscillator always that becomes gapless in the limit when n goes to infinity. This is a universal statement. And the excitation coupling that you need to excite this oscillator is also unambiguously defined. And is given by those formulas. So the rest, of course, we can discuss in each particular case. There may be some interesting technicalities for understanding this boson, etc., etc. This is a good comment, but as I said, there is no ambiguity. There is no ambiguity in defining all the parameters that I'm talking about. So yeah, that's what
we can discuss more on this maybe during the discussion section. If there are more questions, let's see.
Okay. So then we can continue this. I'll be happy to explain more. More technical level. Yeah.
Actually, during the talk, there were a couple of questions from Robert Brandenberger. I don't know, Robert, if you want to ask now.
Okay, yeah, very interesting talk. I just have two quick questions. First of all, in this microscopic picture, there's probably no horizon.
Sorry, say it again.
In your microscopic picture of the black hole, there's probably no horizon at the
horizon is a geometric notion, which is strictly speaking only valid.
Right. So this is very similar to
semi-classical limit.
Right. So this is very similar to in Samya Mattel's fuzzball picture.
I mean, it should be the same. So the fact that black hole should not have strict horizon in full quantum in microscopic theory, I think that should be a universal statement, because horizon is a purely semi-classical notion. I mean, geometry is a purely semi-classical notion. So yeah. So if you have so once we have a theory of a microscopic theory of a black hole, and different people may have different theories, but yeah, one consistency check is that there should not be a strict horizon. But the measure is, so in my theory, I know what the measure is. That's n. So horizon is there up to 1 over n corrections. So in order to resolve horizon, you need to resolve 1 over n corrections. So that's a well-defined statement. But yeah, I fully agree. In any quantum theory, if you have a quantum theory of a black hole, horizon should be an approximate notion. Yeah. Exactly as thermality of evaporation should be an approximate notion. I mean, you cannot have a finite mass object that evaporates exactly thermally. This is simply impossible, because if object evaporates, the energy it changes, and correspondingly temperature should change, and you don't have a strict definition of temperature. If temperature changes, it's always an approximation, and so on. Yes. Mm-hmm.
Great, thanks.
Thank you.
Philip, I see you have a raised hand. If it's quick, otherwise we postpone it. So you decide.
Okay. Well, I had 3 comments very quickly, though. One, when you take the Gross-Neveu model and you look at 1/n corrections, you lose the Goldstone mode.
That's all. That's universal, as I said. What
Yes.
that's a question of definition. So we have to be careful because Goldstone mode is always defined up to 1/n,
Yes.
as you know very well, because the Hilbert spaces of different vacua, they are orthogonal only in systems with infinite n. So therefore, so it's not that you lose Goldstone mode, but what happens is that for finite but large n, the gap becomes 1/n. So in other words, it's not exactly gapless. This is a very important comment, by the way, that you are making. And this is very important to clarify because often there is a confusion about that. So you see, what happens at finite but large n is that you have a mode which is with the gap, which is below all the other modes gaps, but it's still finite. It's 1/n because there is an uncertainty at finite n. There is an uncertainty, and therefore it's 1/n. But I would disagree to qualify this phenomena as saying that there is a no Goldstone mode, because mode is always there. It's just gap is what is changing. So what happens is that strict infinite n limit, the mode becomes gapless. Think about sound waves in this room, right? So in this room, we have sound waves. Sound waves are Goldstone bosons of broken translation invariance by broken Poincare invariance by the molecules in this room. Of course, sound waves are not exactly gapless. Why? Because the occupation number of molecules is finite. The wall has walls, etc., etc. But they are still exist. The sound waves are well defined. So the gap is small, and so yeah. So this is well-defined statement. So therefore, yeah, I would to say that Goldstone mode disappears at finite n. That would be a misleading statement because the mode doesn't disappear; it just gains a gap, small gap, up to 1/n.
Okay. Second comment is related to Luca's question.
To postpone it because we are already 15 minutes.
You're going to postpone now?
Yeah,
There is
maybe
a discussion session, right?
we can postpone the discussion session if it's possible.
Yeah,
Okay.
please. I mean, I would be happy to come back to this. These are very important comments and questions. Yeah, thanks very much.
Okay.
Anyway, hello, Gia.
Okay. Hi.
Let's thank you again.
Thank you. I'll stop sharing.
And we can move to our second speaker, who is Roberto Casadio. Hi, Roberto.
Hey, hello, can you hear me?
Yes, you can hear very well.
Okay, should try to share my screen, I guess, but I'm not enabled yet.
Alex, can you?
You are the co-host now.
Okay, let's see if I can use, can you see my slides?
Sure.
Yes.
Can you still see them?
Yes, very well.
And the pointer as well?
Yes.
Very good. So thanks for inviting me to this conference. It's unfortunate I couldn't come to Portugal too. It would have been much nicer. Somehow my presentation connects to Gia's from the very beginning, because I'll review briefly, very briefly, some corpuscular scalings that Gia and Cesar Gomez made kind of famous a few years ago about black holes or self-gravitating systems in general. But I will then try to refine that picture somehow by giving a more explicit, although sort of toy model description of a black hole made of a quantum matter core, which I think is essential to have a black hole, and at the same time a toy description of the outer geometry. I will do that for the neutral, electrically neutral case described classically by the Schwarzschild geometry, as well for the electrically charged Reisner-Nordstrom geometry, which might not be so interesting from the physical point of view, but allows me to make a few comments about the Cauchy horizon that is present in that classical geometry, which is not in the Schwarzschild case. So since the time is pretty short, let me start from recalling very briefly this corpuscular scaling. I hope Gia doesn't mind if I introduce them. The easiest way to obtain these corpuscular scaling by considering a ball of gravitons. Of course, to assume that this ball of gravitons stays together, you have to include the fact that gravitons self-interact, and you can then start from a very simple energy balance for this system. We have a Newtonian contribution given by the total, let's say, total mass of the system times the Newtonian potential. The usual expression is here. You then have, as I said, gravitons self-gravitate, they couple to each other. You have a post-Newtonian contribution. You can estimate again as a total number of gravitons present in the ball, their energy, and we are assuming that most gravitons have roughly the same wavelength, and of course the Newtonian potential. The Newtonian contribution to the energy is negative, the post-Newtonian is positive. To have consistency with this expression for the Compton relation between energy and wavelength of the gravitons requires that the number of gravitons in this ball scales like the square of the mass of the system in units of the Planck mass. And this is the first scaling relation that holds for any self-gravitating system. We'll see next. Now, if I also assume that the system is a black hole, then this wavelength must be of the order of the gravitational radius, and I obtain the second scaling relation, which, as I mentioned, holds only for black holes. The size of the object must be precisely the gravitational radius. And the second scaling relation is just Bekenstein's area law in a different suit. You can also obtain the Hawking temperature, but I think Gia already derived that today, so I will move on to something a little bit more realistic, at least in principle. Instead of a ball of gravitons, suppose we now consider a star, a real astrophysical object. This star will have a lot of matter in it. Quantum state representing the star is a very large number of excitation of standard model particles. Just to have an idea, for a solar mass black hole, assuming it is just made of neutrons, which is, just to give a number, that's equivalent to roughly 10 to the 57 neutrons. It's a huge number of matter excitations. If we believe in the previous scaling for the number of gravitons in this system, again, the square of the mass in unit of the Planck mass, we get that the number of gravitons involved in the gravitational field is of the order of 10 to the 76. And the complete quantum state describing star and its gravitational field is going to be a complicated and tangled quantum state containing roughly this order of magnitude of excitations. There's two lessons to learn here. The first one is that any realistic description of a process like the gravitational collapse that leads to the formation of a black hole is probably impossible. Well, I would say it's definitely impossible. So we need to rely on some toy description. And in the following, in fact, I will present a toy description for the matter core and a toy description for the gravitational field generated by this matter core. Another lesson is that these two components, these two ingredients in the complete quantum state are entangled. Whatever unitary evolution then leads to the formation of the black hole cannot make that entangled state into a product state in which gravity and the matter state are just product one of the other. This would lead inevitably to the existence of quantum error, the fact that this factorization doesn't happen. And in the next presentation, I think Xavier is going to tell us a way to compute the presence of this quantum error. But for my talk, what I want to do is just, again, give a simple toy model description for the star or the collapsing body and a toy description of the gravitational field, connected together by very little information, not by solving complicated gravitational equation that I don't know how to deal with when the number of excitation is definitely that large. So first point, the quantum dust core. Simplest model of gravitational collapse that we know is the Oppenheimer-Schneider model. The ball of dust is made of particles that interact only gravitationally. There's no other interaction in there. This can be solved analytically in general relativity. What I want to do here is give a quantum description that preserves some nonlinear features of general relativity to begin with. And of course, I'm not going to describe the evolution of each speck of dust in the system, because again, that would be 10 to the 50 something excitation. I wouldn't know what to do with it. So I reduce the system to one effective degree of freedom, which is the radius of the ball. This is what we do usually in general relativity when we solve for this model. The radius of the ball follows the geodesics in the outer Schwarzschild space-time. This is the classical picture that we have. This expression is not exact. There are coefficients there that are sort of arbitrary, order 1. I haven't included them for simplicity. But that's qualitatively the equation that governs the classical evolution. I can put that equation in the form of an effective Hamiltonian, and I can solve it as a time-independent Schrodinger equation to find the spectrum of bound states. Again, here I'm describing the ball by means of an observable, presumably observable quantity, which describes the system classically, but has no clear-cut relation with the fundamental degrees of freedom, which would be, the quantum field excitations of the components of this ball of dust or ball of particles. Now, it's easy to find the spectrum for the Schrodinger equation. Of course, it's like the hydrogen atom. And in fact, if I forget this expression you see here, which comes from general relativity, and just call this quantity E, the eigenvalue of this Hamiltonian, I would obtain a Newtonian spectrum. In fact, that equation would be energy conservation in Newtonian physics. And the Newtonian spectrum is like the hydrogen atom spectrum. It starts from principal quantum number equal 1, which would correspond to expectation value for the size of the ball, which is a tiny fraction of the Planck length. See, for a large macroscopic core, this is essentially a vanishing fraction of the Planck length. This is a singularity in my book. However, we are not starting from Newtonian physics. We have to include some degree of nonlinearity from the theory. And GR tells us that, well, there is that expression for the eigenvalues that must make sense. In particular, this block E classically would be the conserved energy along the geodesic, must make some sense. If you require that it keeps making sense even in the quantum theory, what we get is a lower bound on the principal quantum number that in fact scales exactly like the corpuscular relation. Noting that here there's not much about the way I introduce the corpuscular scalings. It's completely different derivation, but still I obtain that the matter core ground state scales somehow is determined by the mass in unit of the Planck mass squared. The rest of the spectrum below this principal value for the principal quantum number is not there, it's not physical. This is a sort of classicalization in action. Correspondingly, the minimum expectation value for the radius of the ball that I obtain is of the order of the gravitational radius of the ball itself. It's macroscopic. There could be a factor there, numerical factor. Doesn't matter whether it is, I don't know, 1,000 or 100. Wouldn't change qualitatively the picture. I could show you more precise expression, but they don't change much. So here you see, just assuming this form, and I cannot really go very large in mass because these are Laguerre polynomials. The wave function is given by Laguerre polynomial with many, many nodes depending on that number. N equals 16 means 4 times the Planck mass for this core. So it's still a very small core. This is the probability density to find the radius of the ball of a certain size. From the Newtonian point of view, you would start from here. This is the ground state. It's peaked somewhere inside the gravitational radius. So this could be, in fact, the core inside the black hole. And as you increase the principal quantum number by keeping the mass constant, so you consider so-called, somewhat excited states, you would find that the ball gets larger and larger eventually outside the horizon, and it's no more a black hole. The ground state generically is inside. Some other states could be for very large mass. All of them, well, we are still analyzing entropy property. There's a generalized uncertainty principle you can derive from this. But let me stress the fact that the only information we can extract from this wave function essentially is the expectation value of the radius of this matter core that is supposed to source the black hole geometry. Because the toy model is designed precisely to give that information and nothing else. We don't know how the particles are distributed inside the ball and so on and so forth. We have restricted the description to the minimum amount of information we need. Now, we can next look at the gravitational side of this self-gravitating system, particularly the geometry outside or corresponding to this matter core. And for that, here I used Schwarzschild. I was assuming that the ball is in an empty universe. For reasons that will become clearer later, instead of the Schwarzschild geometry, I consider a Schwarzschild de Sitter geometry. So beside the usual mass term, there's also cosmological constant. Now, keep in mind that we apparently live in a quasi-de Sitter universe, so this makes physical sense. But there is another reason I introduced, the de Sitter part, that will become more clear later on. I require that the gravitational radius of my collapse core is much smaller than Hubble cosmological horizon radius. I want a small black hole in a very large universe to describe something more similar to what we actually see around us. You can find in this paper more about why considering Schwarzschild de Sitter is so interesting, particularly for dark matter, but I don't want to go there. It would take too long. Now, how do we come up with a toy model for the quantum state that is supposed to describe this geometry in some mean field approximation? Because that's a classical geometry. I want to find a quantum state that reproduces this geometry as an expectation value of some observable. And keep in mind that I have these scaling relations inside. Now, one way to obtain that toy model quantum state for this Schwarzschild or Schwarzschild de Sitter geometry is first of all to start from defining what would be the absolute vacuum in quantum gravity. And I would say that it doesn't really matter much, but the absolute vacuum in quantum gravity should be a universe completely empty, with no matter excitation, no gravitational excitations. And therefore, you could describe it as a Schwarzschild, or sort of as a Minkowski geometry, or of any dimension, really, because if there is nothing in that manifold, you cannot really tell points apart, nothing happens in it. Even saying that it's Minkowski in 3+1 dimensions doesn't make much sense because nothing happens, time has no meaning. But just for the sake, again, of simplicity, let's take Minkowski in 3+1 dimensions, and time doesn't matter much here. In fact, I want to reproduce this geometry, which is static, like the core I'm going to use to source this geometry. I could just consider a static case. Spherical symmetry, it's convenient to use J0 Bessel functions. You know, it's like adapted form of Fourier transform to define my normal modes in this vacuum, satisfy the usual relation, creation operator, so on and so forth. Whatever geometry I want to reproduce, it should be created or correspond to excitations of these modes somehow upon this vacuum. So I build excitation on this vacuum and I try to obtain the geometry I wish to have. Geometry I wish to have should be very close to classical, and therefore it's natural to use coherent states for this scalar field that's supposed to mimic the geometry. It's pretty much the best we can do. Coherent state is defined in the usual ways that an eigenstate of the annihilation operator. When I take expectation values on a certain coherent state, this is what I get. And in particular, I want this expectation value to reproduce the particular metric potential, particular metric function of interest to me for my system. I need to kill the time dependence, and therefore I need to choose those phases in a suitable way, but that's not particularly strange. You know, a static approximation is indeed an approximation. Nothing is really static in our universe, but if we want to obtain some sort of potential, and the metric is a form of potential, we need to freeze the time evolution. So nothing strange there. Now, what is important? Whatever coherent state I introduce to describe the metric function, the geometry, it must be a well-defined quantum state. And in particular, a condition for this state to be well-defined is that it is normalizable. Or in other words, for a coherent state, the total occupation number given by this expression, if I look at those coefficients, the square of them actually, as the single mode occupation number, integrating on all of them, I obtain the total occupation number in that coherent state, which is a measure of the distance from the vacuum. The larger this total occupation number is, the farther away I am from the proper vacuum. But no matter how far I get, it should be finite. Otherwise, this quantum state is not well defined. Apply this machinery to our Schwarzschild geometry. In particular, I need to reproduce this metric function here. Is it to get the Fourier transform? Is it to obtain everything explicitly? Now I compute the total occupation number and I find that it diverges. If I assume that my coherent state is supposed to reproduce the entire classical geometry everywhere. If I use this expression, plug it into the integral gives me the total occupation number, this will inevitably diverge. This tells you immediately there's no quantum state so defined that can reproduce exactly the classical geometry. Whatever quantum state is realized in nature, sourced by that core, for example, that I described before, it must depart from the classical geometry. How? Well, it must depart in the infrared and the ultraviolet. Exactly how it departs, and to answer that question, I should know exactly how the core is made, how it determines the gravitational quantum state by solving very complicated expressions. I'm not quite sure how to do that for realistic cases. So here I just use the minimum information that I obtained from the description of the matter core. I know the matter core has a certain average size in its ground state, order of gravitational radius. I use that to define an ultraviolet cutoff for that integral. I know above that scale, the real g of k in my coherent state must depart from the classical behavior. And then I will have to introduce an infrared cutoff to get rid also of the infrared divergence. And that's why I need the sitter. We'll see it in the next slide. Whatever those cutoffs are, again, they should not be taken literally. It's just a sign of my ignorance. I don't know better than this so far. However, I change that integration in the infrared or in ultraviolet, I will get a function here of the ultraviolet and infrared regime that really depends on how I cure those divergences. I shouldn't need to do that if I knew what the G of K really are. Told you about the ultraviolet. For the infrared, now I use the fact that my object is inside of the sitter universe. There is a cosmological horizon, and therefore I define my infrared cutoff as the inverse of the cosmological horizon. I have those two cutoffs. I know the integral, I know what to integrate, and I can get a quantum corrected metric function by simply summing overall modes with those cutoffs. This quantum corrected metric function for those sharp cutoff, which are again very simple description of what I'm trying to do, will inevitably lead to some departure from the classical metric function. And here is what they look like, again, with sharp cutoff. To be more clear, what did we obtain? A scaling for the number of gravitons in this quantum state that depends, in fact, on the square of the mass of the system in units of the Planck mass times a function which leads to corrections. In principle, the mass enters in the logarithm. Doesn't need to be a logarithm. It could be another function. I don't know exactly what function it is unless I can, again, solve exactly for the entire system. Reason I don't reproduce that extra function here. Let's say I have some, I'll just leave it apart. From the other quantity here, which is the expectation value of the radial momentum, suffers only of ultraviolet divergence, but it still plays the same cutoff because it's the same quantum state. If I correct it to control this quantity, I must use the same cutoffs here. You see, that's what you get. And from this ratio, you obtain the typical or the average wavelength in the gravitational geometry around my core. And that's, again, turns out to be similar scaling and as the one from the corpuscular picture. But again, there would be corrections that I'm not showing because they are really highly model dependent. Now, what does the metric look like once I use this quantum corrected function, V, QM? This is what it looks like. Here, the dashed line is the Schwarzschild solution. Sorry, there should be an M there, but not an N. So this is the Schwarzschild V equal to -1/2 in correspondence of the horizon. This is the quantum corrected with the sharp cutoff metric function. There are oscillations around the classical expression, which are due to the sharp cutoff. If you use a smoother cutoff, you would not see oscillation, you would see something else. The amplitude of those oscillations really depends on the inverse of the ultraviolet cutoff, that is the, let's say, the radius of the core that I'm placing inside. But no matter how small that core is, as long as it is finite, if I trust the reconstructed metric everywhere, including there where the core is and it's a quantum object, presumably, maybe it doesn't make much sense to think in terms of classical geometry. If I still do, I find that it's really regular, no matter how small that core is, again, as long as it is finite, and it cannot be a singularity, as I showed you before. In particular, some of the scalar invariants will still diverge, but tidal forces will always be finite in the center. So it's perfectly regular. And unlike several proposed regular black holes in the literature, it shows no inner horizon. There's no Cauchy horizon ever for any value of this core size. I think that's an important feature too. Inner Cauchy horizons are not any better than the point-like singularity that you find in Schwarzschild. They are quite nasty objects. you know, you can only travel from inside out, and they give rise to various phenomena that have been studied, like a mass inflation. So to see whether this quantum description of the geometry could help with Cauchy horizons more in general, we also studied the Reisner-Nordström metric. So suppose now your core has charge, and for simplicity, we place the charge right in the middle, in the center, because to distribute the charge inside the core some way would require, again, making a choice of how the charge is distributed. So the charge is in the very center, but the core will have finite size. Outside this core, classically, would have the Reisner-Nordström metric, which contains two horizons, provided, you know, the charge Q is sufficiently smaller than the mass. So this would be the classical picture. This is the classical Reisner-Nordström metric function there, equal to -1/2, where the two horizons are. There's the outer event horizon and the inner Cauchy horizon. Now, repeat the same quantum description that I gave you before. You have those two cutoffs. The infrared doesn't matter. You can send it to infinity, actually. But the ultraviolet does matter. Ultraviolet, again, I interpret it as the inverse of the size of the core. If the size of the core is in between the two would-be classical horizons, you get a picture exactly like we saw before for Schwarzschild. The center is regular, meaning, yes, some scalar invariants will diverge, but all the tidal forces remain finite. And there is no Cauchy horizon. Therefore, there is no mass inflation or other nasty phenomena that have been studied in the past. It's only if you allow for the core to be smaller than the would-be classical inner horizon, then yes, you recover one or even more, depending how you define your cutoff in the ultraviolet. You could have one or many more horizons inside. But then that situation doesn't look particularly realistic to me, for the fact that you would need your inner core to shrink below this inner horizon, and we know classically that cannot happen because everything that falls in stops right there. So for me, the physical case or more physical case is represented by this picture here, where again, you don't have an inner horizon, only the event horizon and some departure, strong inside, potentially extremely small, unmeasurable outside from the classical geometry. Now, I don't know how much time I have, but I'm practically finished.
5 minutes. 10 minutes.
10 minutes. Oh, I went very, sorry? 5. Well, I went very fast, so I can come to the conclusion, actually. What we've seen that two toy models to describe the matter core that sources a black hole geometry and the black hole geometry itself. The matter core appears to be quite reasonably, I don't know if you agree with me, described by the ground state, which is very far from the vacuum, meaning in this particular description, the minimum quantum number of that ground state, again, is proportional to the square of the mass in unit of the Planck mass. It has, keep in mind that that calculation has nothing to do with the corpuscular estimate I gave before. It comes from a different perspective. Gravity is, however, there, and particularly nonlinearity of general relativity, or some of it, is embedded in that description. The core never becomes really a point-like singularity. Even if we ignore all other forces that would give probably extra repulsive contribution in a more realistic description of the core. The black hole geometry, as we have seen, again, it's very far from the gravitational vacuum. For, again, the total occupation number scales like the square of the mass of the system, unit of the Planck mass. This is the corpuscular scaling that I showed you at the beginning. Quite remarkably, the two scalings coincide. for the matter core and for the geometry. And I still have to understand if there is something deeper in it. Simple preliminary estimate, for example, of the entropy that you can associate to the matter core, and the entropy, well, that's easy. The entropy for the black hole geometry is precisely what you expect from the Bekenstein area law. The one for that ground state seems to be smaller or to increase slower with the mass, in fact, which would be consistent with our idea that the entropy contribution coming from matter to black hole is less important than the one coming from the gravitational part, indeed. Then another result is that by putting together these two pictures, we have no singularity because the core is never point-like. There are no Cauchy horizons, most likely, even in the charged case. And the next step would be to go from charged black holes to rotating, I think more interesting, rotating black holes, because in nature we see all the black holes we see probably rotate as some spin. And I expect the similar results to be obtained, again, no inner horizon. And then at some point, here everything is static. In these two descriptions, both the matter core and the outer geometry are described as static states. Would be very interesting to consider some time evolution, but that is going to be a lot more complicated, I'm afraid. Now, that's all. Thank you.
Thank you very much, Roberto. So actually, we have time for questions. So first was Gia.
Hi, Gia.
Yeah. Hi, Roberto.
Hey.
Hi. Yeah, I was just trying to understand to follow if we because I mean we have studied many of those topics back with this large N. I want to make sure I understand and whether we are on the same page, because for instance, when we talk about matter, contribution from matter into a black hole, indeed. So what happens is that the black holes that are not extremal, they have always the occupation number of matter particles much less than the occupation number of gravitons. For example, Rice-Nordstrom black hole, if it's extremal, then the occupation number of photons in the black hole is equal to occupation number of gravitons. So basically, that's the way to understand extremality.
Okay.
In this language. So in the corpuscular language.
Yeah.
But
you don't see it here. Yes, the reason, again, let me make it clear. These wave functions that I obtain here when I describe the core, those principal quantum number is not an occupation number. It doesn't count the number of particles.
No, that's precisely what I want to ask, because you see, at some point you are departing because then you are making some extra assumptions and extra.
Yeah, I can tell you we are computing the entropy, configuration entropy for this matter core. And what I can tell you preliminarily is that it grows with the mass slower than m squared. So yes, the occupation number that you can infer from computing the entropy for this wave function is smaller than the entropy that you obtain from the gravitational part of the system.
No, I mean, I understand, but so yeah, actually, that's what I don't understand, because I don't understand how you can make universal statement about the matter contribution into the entropy unless you know what the properties of matter
they are not. I'm not saying they are universal. I'm saying we are trying different way of implementing this wave function that would correspond to different distribution of matter inside the core, for example. And we
understand, but I mean, what I'm saying is that matter can have its own entropy because it carries some quantum numbers. So therefore, the entropy of a black hole depends on the quantum numbers of matter particles that it swallows. And again, there is a bound. Extremality comes when the entropy of matter part is equal to the entropy of the gravitational part. So that's one way to see why you cannot have a black hole of entropy that exceeds the gravitational entropy. So gravitational entropy is always the limit. These are universal bounds. So I assume you should obtain the same once you specify the entropy of the matter. But my question, in order not to take to infinite time, because at each point I would like to understand what is the outcome. But what I don't understand is, when we talk about entanglement, right? So the entanglement takes time to develop. So in other words, if I, for instance, even without matter, when I have a state which consists of many elementary constituents, even if I start with an entangled state, eventually at some point entanglement develops and reaches some maximum. So therefore, so in other words, with our studies, we studied this through the series of papers, how fast the entanglement can develop in graviton state, in graviton plus matter. And so what we see is that, so typically if you have a system which classically doesn't have Lyapunov exponent, meaning that doesn't have classical instability, the entanglement time is pretty long. It's approximately half decay time. If you have a system which has classical instability, then the entanglement could be faster. So therefore, but here you don't. So you don't make any reference to the time scale.
No. Here I'm not.
Over what time scale you?
There is no time scale yet. This picture is completely static. As I told you, I have no Hawking evaporation. I'm just setting the stage for computing all of that.
No, but then your entanglement will be whatever you will start with. I don't understand how you can evolve. Because you see, when we are considering, I'm asking something really totally trivial. I'm just saying, if I have a simple system, let's say this iPhone here or something, whatever, this phone, which has many constituents, I can start with a system with some initial entanglement. That's an input. Sure. But what is interesting is that if I start with some minimal entanglement among the constituents, how fast the entanglement develops. So if your system is static, then of course entanglement is whatever you will simply put at the beginning, which is of course it's fine, but then this what confuses me. I don't see how you can make a universal statement whether ground state is entangled or unentangled, because
I'm not trying to make
crucial to evolve in time.
Yeah, but I'm not trying to make. I'm not sure I understand the question. I'm not trying to make universal statements about entanglement. My way of looking at things is, if you want a black hole, you have to let the star collapse.
Yeah.
Okay. The star is a very complicated object which will contain a lot of entanglement.
Yeah, but the star entanglement normally is minuscule compared to the limit. So in other words,
that's what I would like to find out.
Trying to ask, because the entanglement has certain limit. If you have a system with n particles, you cannot make it more entangled than everybody with everybody. Entanglement cannot be bigger than n if you have a system of n elementary constituents.
Of course.
So there is a maximal entanglement in each system. So now, if you take star and ordinary star, and if you compare the entanglement of the star with the limit that such a system could have, which is, by the way, the saturated system. Saturated system is the one that can also have maximal entanglement. That is very low compared to the maximum. So in other words, we can safely conclude that entanglement of the star is minuscule. So now if you put a star and you will wait.
So you're telling me that you have 10 to the 57 particles and 10 to the 76 neutrons. They are all entangled in a way that explicitly nobody has computed. That's very small.
No, they are not all entangled. That's what I'm saying. It's extremely hard to make a macroscopic system maximally entangled. That's why we don't, you see, this is a very important point. The point is, macroscopic systems ordinarily, they are very far from entanglement. That's why macroscopic systems are classical in a very good approximation. Now, there are exceptions. There are systems that are maximally entangled, and these are saturated systems. So black hole can become maximally entangled, self-entangled, I mean, but that takes some time. That's what I'm trying to say. The star, no matter how long you will wait, will never become maximally entangled.
Well, I guess
why,
it
because
depends.
Star is not a saturated system. That's the difference between star. Star is not a saturon. So
okay.
So
how do you form a saturon? Sorry, how do you form a saturon?
Sorry.
How do you form a saturon then, if not by collapsing something?
Yeah. Once you collapse, then it once you reach the saturation. For example, a black hole. If you take a star and you form a black hole, black hole is a saturated state, and now black hole can reach maximal entanglement. Yes. But it takes time. So
yeah, from the point of view of an outer observer, which I assume is the one who would measure the entanglement, it takes an infinite time to reach the black hole state.
No, we're talking about quantum. We're talking about quantum theory. Quantum theory. There is a time scale which is finite, and over that time scale, and this time scale is given by the half decay time of a black hole. So after half decay time, black hole remaining black hole state can be maximally self-entangled and also entangled with outgoing quanta if you keep them somewhere nearby. So yeah, for black hole can maximally entangle. What I'm trying to say is that maximal entanglement is not for free, and the fact that we have a macroscopic object doesn't mean that we can entangle it maximally, because most of the macroscopic objects, they have an extremely low entanglement. It's very fragile. You see, even if you try to prepare it in highly entangled state, it will collapse into something which is not entangled. So this is this is important. This is very important. But okay, I mean, since you are not studying time evolution.
Not yet. That's what I was planning to do.
This is not a complaint or anything, but I'm just saying you should take this into account, because this has been studied.
No, I will. That's part of the project, to understand what happens but first I have to make it more explicit than what I showed you. Again,
I mean, there are other things, but I let other people ask questions. Yeah. Thank you.
Thank you.
For later. And there is a question from Philip.
First of all, Roberto, good morning. Thank you for your talk. My questions are lots more straightforward. You mentioned in your talk that you thought that the vacuum didn't know anything about curvature.
Yep.
But if I calculate the expectation value of T mu nu in the vacuum, it's proportional to the curve space metric, not to the flat space metric.
The way I see a curve metric is similar to, I mentioned there, loop quantum gravity, Regge calculus, or whatever. If the space-time is curved, it means there is an effective geometry. It means you are not in the proper vacuum. I know people tend to think, the Schwarzschild metric is a vacuum solution. No, it isn't. You need a source somewhere. And you need, from the perspective of quantum field theory, it means you have virtual gravitons around the source. No, that's not the vacuum. For me, vacuum, I mean an absolute vacuum, where you have no gravitational excitation, no matter excitations. If you compute an energy momentum tensor that is not zero, then that's not a vacuum, by my definition. I know that's clear.
Okay, so if I quantize a fluctuation h mu nu in terms of A's and A daggers, what you're calling the vacuum is not the state that A annihilates.
No.
Okay.
If you only quantize fluctuations, you are assuming the background field method. That's not what I do.
Okay. So how do you make contact with the cosmological constant?
Oh, that would be topic of another. But yeah, you can find some details in that paper. Yes, that means the universe, is being the sitter, is not a vacuum. It's a quantum state. Sorry, the paper is this one. This one here. You have a quantum state for the universe, which is not a vacuum solution. Technically, you don't have exactly a cosmological constant. You have, there's a corpuscular picture for that too. Yeah, might agree or not. Yeah, it's a quantum state, but it's not the vacuum as I define it, a space or a universe with nothing in it.
Okay, anyway, I don't want to get into a big discussion now. We can do that afterwards.
Sure.
But
I'll be happy to.
Can you fit the accelerating universe data?
Yes, can do it.
Okay, well, maybe you'll tell us about that afterwards. Thank you.
Yeah, thank you. Oh, I don't have all the details, okay, but for static snapshot, I can do a lot of things.
One last question from Alessia, and then we can postpone everything to the discussion because we're a bit late. So please, Alessia.
Yeah. So Roberto, hi. Can you hear me?
Yeah, I can hear you. Go ahead.
Great. So thanks for the nice talk. So as you know, I'm particularly interested in these oscillations that you see because this type of metric also arises in some cases from higher derivatives. And so I have some questions in this direction. So first, if these are really tied to your particular regularization of that integral, so the fact that you introduce a sort of UB cutoff, and what happens if you send this cutoff to infinity, so if you squeeze the oscillations, and also what would happen in more refined approximations. This is my first question. And the second one is more about your starting point. So you have a static system. You are not yet studying time evolution. So in what sense the horizon is fuzzy? Because I mean, you can identify a specific point.
Fuzzy. Okay. Yes. First question is easy. You cannot send the cutoff to infinity because then you would have diverging total occupation number. As I mentioned, the cutoff is just a sign of my ignorance. I don't know exactly how to model this gravitational state as it should be connected to the matter core inside. You can play with different density distribution for the core, and you will get slightly different form for the quantum corrected metric. Okay. Some features are totally dependent on the particular way you cure that integral. This isn't. No matter how you describe your core, as long as it is not irregular, you always get that behavior in the origin. That's the generic feature. Now, why did I say that everything is fuzzy in a sense? This, what you see here, the expectation value of that scalar field that reproduces the geometry, there are, of course, fluctuations around it in the quantum state that you can compute. They are usually, well, depend on this cutoff. If the cutoff is the size of the core is very small, the fluctuations around the horizon are totally negligible, and that's pretty much what I expect for a macroscopic black hole. But in principle, and I was thinking in that case, in particular, a small black hole or a black hole that evaporates ideally and becomes small. At that point, the quantum fluctuation in that quantum state will become so large that this expectation value or the mean field approximation is not reliable anymore. In general, it is never sharp in a sense. There's always small quantum uncertainty in the position, or if you wish, in the geometry, in that sense. But phenomenologically, unfortunately, not very, very large.
I see. But so would you still think that these oscillations, even outside of the region where you cannot really parameterize very well the core, are a universal feature of the corpuscular?
I think, no, the deviation are a universal feature. The shape of the deviation, whether it is oscillations or that really depends how you describe the core.
Okay, thanks.
Okay.
And yeah, okay. Yes,
yeah, since maybe it's quite late, we can postpone further comments and questions to the discussion. It's a big deal. Better to postpone. Okay.
Okay.
So let's start again.
Thank you. How do I stop sharing? Okay.
And we can move to our third speaker of the second session.
Okay.
With Xavier Calmet.
Okay.
Hi.
Hi, Xavier. How are you?
So good, thank you. I can't share the moment.
Yes.
No, okay. Sorry, I couldn't find the button to stop my sharing. Now I did.
All right, let me find a full screen, please. Right, can you see this?
Yes, perfect. Please, you can start.
Okay, well, thank you very much for the invitation to speak at this meeting. And I'm sorry I can't be there in person. It's just the middle of the term here. So I'm going to tell you about some recent results on quantum hair that we obtained with Steve Hsu, Roberto Casadio that you just heard, and a very talented PhD student at Sussex, Volker Kuipers, who's just finishing his PhD. He's got his Viva next week. Sorry, trying to find how to swap. Here's the outline. I'll give you an introduction to the methods we'll be using, which is basically effective field theory applied to quantum gravity. And I apologize to the experts. I put it really at the level for grad students so that if there are any, they know what I'm talking about. And then we'll come to an application of these calculational methods, and we'll calculate the gravitational potential of stars and extract that of black holes from this result. And basically, I will show you that there's a quantum hair that we can calculate within these EFT methods. And then I will draw some more general conclusions about the quantum states of the graviton. And then we'll get into black holes, and I'll tell you what we've learned recently about black hole radiation and evolution, and we'll come to the conclusions. So it's often believed that we can't do calculations on quantum gravity, and I do not fully share this point of view. As long as you know what you're doing and you're working below the Planck mass, there's a very well-defined procedure to do that. And the question really goes back to the old question of how to describe general relativity at the quantum mechanical level. And you all know that if you just linearize GR, you end up with a theory that is not renormalizable. And that's why people look for UV complete theory, like string theory, look on gravity, and you name it. But again, the goal of this approach with EFTs techniques is to understand how much we can understand with quantum field theory. I would say that we may not care so much about understanding physics beyond the Planck scale because it might just be hidden from us. We've got good reasons to think that length scales that are smaller than the Planck scale are not observable because you would form small black holes. So we might not be able to extract any information from distances shorter than the Planck scale. So from that point of view, all we might care about are effective field theories, and that may just be what we need for all practical purposes. So again, the link here is to, or the goal here is to make the link with observable. So we want to calculate things that in principle could be measured. Obviously, in most situations, because quantum gravity, things turn out to be very tiny, but at least it's a proof of principle that we can do calculations in quantum gravity. And in some cases, it may lead us to some thought experiments that can be useful to try to maybe get to the UV complete theory of quantum gravity one day. What I like about it is that it's very conservative. You don't have to assume anything crazy. You're just using techniques that we understand very well, that we know work very well for gauge theories in a standard model. So what we're going to assume is very minimalistic. We assume that GR is the correct low energy theory, which I don't think many people would dispute. We're going to assume general covariance invariance. That means that the quantum gravity has only 2 degrees of freedom, which are basically the massless gravitons. They're 2 LST states. Then we have to assume what we put in our T mu nu. So that's on matter theory, and that could be whatever you want to work on. It could be the standard model, your unified theory, inflation, you name it. Here for the stars, we'll assume some energy density. And with that, we are in a position to write an effective action for quantum gravity. So really the program goes back to the 60s and Feynman, who just basically adopted a shut up and calculate approach to quantum gravity. He linearized GR and was trying to find observables and see again what could go wrong. And again, looking for consistency conditions. So things have improved over the time. They were major contributions from Wilkowinski and Barwinski in the 80s. Donahue took over in the 90s. And I think we've solved some of the remaining issues more recently. So again, going back to really the basics, and I apologize again for the experts, but that may be beneficial for younger people. You know that Einstein's equations are given by the following: R mu nu minus 1/2 R G mu equals 8 pi G T mu nu. And we have the Ricci scalar, the Ricci tensor, and they contain two derivatives of the metric. And that's important because that means a mass dimension 2. And the reason why I'm going through this exercise for the younger people again is that it tells us how to organize the effective field theory. So Newton's constant here is related to the Planck mass. Again, T mu nu is the energy momentum tensor, and that's your particle physics model or your star model, whichever you want to take. And you know that you can derive these equations from the Hilbert-Einstein action, which is simply square root of G2 over kappa squared R. And again, the dimensions of the invariance you can write R mu nu squared and so on is important to tell us how to organize our effective action. So when you start to calculate corrections to the Hilbert-Einstein action, you will use what is called the unique effective action methods, because it gives us a way to get gauge invariant Wilson operators. That's really the contribution of Willis-Kovinsky and Barvinsky in the 80s. So there's a well-defined procedure that tells us how to get an effective action that is fully gauge invariant. So you can organize your action in terms of a curvature expansion. And that's what I've done here for you. So you have the Hilbert-Einstein term. If you took the standard model, you could have the non-minimal coupling of the Higgs. So Higgs will be the H will be the Higgs doublet here. Size dimensionless. You have a cosmological constant. Then you get R squared, R mu nu, box R. And then you're going to get terms that are of the shape R log box over mu1 squared. So that's our normalization scale. R minus B2, R mu nu log box, mu2 squared, R mu nu, and so on. And you can think of this as an expansion in curvature or in the scale m star up to which you trust your theory. So the beauty of this approach is that the value of the Wilson coefficients of these non-local operators here, so with the boxes, log box, are calculable, and they are a universal predictions of quantum gravity. So basically, depending on how many scalar fields, fermions or vectors or graviton you integrate out, you will get different values for B1, B2, B3. And again, if you use the unique effective action approach, you get a well-defined prediction here. So that is really what is exciting about it, because if you have an observable that depends on these non-local operators only, you can get model-independent predictions from quantum gravity. Now, the price to pay for this is that the local operator, the Wilson coefficient of the local operators, C1, C2, box R won't matter because it's a total derivative, but C1 and C2 are not calculable unless you know the UV complete theory. So that's the price to pay. So with the EFT approach, we'd have to measure C1 and C2. And obviously, there's an infinite number of such Wilson operators that you have to measure depending on the order in curvature in which you expand your EFT. But again, as long as you are lucky enough to find an observable that depends on the right operators, then you have a prediction that should match whatever you predict in string theory, loop quantum gravity, you name it. So, sorry. What does this log box stand for? So sometimes there's confusion in the literature about this. What we mean by this is really the Fourier transform of the log minus p squared that you have from your Feynman diagrams, for example. And in the end of the day, this is a distribution. So in flat space-time, and for dimensions, that's the expression you're getting when you massage this term. So, sorry. Basically, what I'm trying to convey is that this is a well-defined approach. I don't have time to go into more details of how you develop these distributions, but that's in the literature by now. And again, that enables you to do calculations. So you could ask yourself, well, what field content do I have in this EFT? There are two ways to discuss this. The first one is to linearize the EFT, or you map it to the Einstein frame. But basically what you find, if you squeeze your Green's function between two classical sources, is that you get the massless gravitational wave. Basically, you get massive spin 2 wave and massive spin 0 wave as well. So you can calculate the masses of these objects by looking at the poles, and basically the poles are given in terms of the of these Lambert function, the W, which is funny, it appears very often in the expression of this type in quantum gravity or when you use some logs. So there's a whole literature on these Lambert functions. And basically what you find is that these objects have a mass and a decay weights because they have a complex pole. And again, I don't have time to go into the details, but if you wanted, you could remove poles that don't have the right properties by choosing your contour integrals properly. So very quickly, you can ask yourself, well, what do we know about bounds on these extra poles? Well, they would modify Newton's law, the 1/r. So you would get some Yukawa term. And again, the standard way to bound this is to look at Udvash. And you basically know that if you have a coupling constant of order of that of gravity, which is the case here, you get a bound of 10 to minus 3 eV or 10 to minus 2 eV by now. So that's what we know. And anything heavier than this is fine. You would not have seen it. So you could ask yourself, well, sorry, I anticipated this slide a little bit. So when you add the contribution of the spin 0 and spin 2 part, you notice that the imaginary part of the masses cancel out, so the potential is real as you expected. And again, Udvash tells you that you have a bound on these masses. Now, sometimes people in the string community try to get rid of the ghost by making these two contributions cancel out. It's not easily feasible because these experiments like Udvash or these torsion pendulum experiments do measurements on different scales, distances, basically. So if you had a cancellation on one length scale, it would not happen on other scales, and you would have seen the effect. So this is clearly not the way it works. Now, I will say just one word. The ghost in the EFT is not an issue because it's a classical field and nothing bad happens. There's no instability. So one last slide on the bounds on the parameters of this EFT before we get into stars. So you can, again, that's basically the local part of the action that I was showing you. So in the standard model, for example, you will get a contribution from the Higgs vacuum expectation value. So m squared and psi v squared have to combine to give you the Planck mass. We don't have anything new to say about the cosmological constant in that framework. It's just a parameter to measure. C1, C2, well, those are the bounds from Udvash that I mentioned. So that's they're basically dimensionless constant. That's what's interesting. And we know that they should be smaller than 10 to the 61. That doesn't look very impressive, but when you think in terms of masses, that's 10 to minus 2 eV, which is much more constraining, obviously. To put things in perspective, if you want to do inflation based on R squared, you need a C of 10 to the 8. That's Tarwinski's inflation. Obviously, we're far from probing that with pendulums. From the fact that the Higgs behaves like the Higgs boson and doesn't decouple from the rest of the particles of the standard model, we had set a bound some years ago on psi of the order of 10 to the 15. And again, we're far away from probing inflation, but again, it's interesting. We can get some limits on these parameters. And again, m star here is going to be the expansion parameter, if you want, or the scale up to which you can trust your EFT. That is the scale up to which quantum gravitational effects become strong. And from searches of quantum black holes at the LHC or in cosmic rays, we know that m star is at least 10 TeV, roughly speaking again. So that's what we know about this EFT framework. And again, there's been a lot of work invested in the last 20 to 30 years in that direction. And we are now in a position where we can make some calculations in a rigorous way. So we start from the unique effective action, and I've reproduced it here again. I'm sorry I've swapped my notation for the Wilson coefficient of the non-local part. That's why we reproduced it again. I was too lazy to write all my slides. I apologize for this. So we've got alpha, beta, and gamma here as the Wilson coefficients of the non-local operators. And you've got C1 of mu, C2 of mu, C3 of mu as the Wilson coefficient of the local operators. So you know that if you vary your action with respect to the metric, you'll get Einstein's equations at tree level if you want, and you get the corrections, the leading order corrections, quantum gravitational corrections coming from the local and non-local part of the action. And basically, I want to point out that the log box appears here, acting on R, so the Ricci scalar, Ricci tensor, Riemann tensor, and that's where you have to, depending on the problem you're looking at, pick the right distribution for log box that depends basically on the boundary conditions you have in your system and also on the number of dimensions you're having, if it's a space-time dependent problem or not. But we know how to handle these things by now. So basically, we can calculate these tensors, and we can we have expressions for this distribution, so we can make calculations. So let me apply this to calculate the corrections to the metric of a stationary, homogeneous, and isotropic star, and we're going to fix the radius to be Rs, and the density given by rho naught times a step function. So basically, there's a constant density inside a star, and outside is nothing. So the solution to the tree level part of the Einstein equation is very well known. So inside the star, it's so for R spawn and Rs, it's the interior Schwarzschild metric that I've reproduced here for you. And we've got a Misner-Sharp mass that is given by an integral over the density, which again is trivial here. It's just a constant density. So we know the metric inside. We also have the metric outside, which is given by Schwarzschild. So then the procedure consists in doing some perturbation theory to solve our differential equations. And we do perturbation theory around the classical solution that I've just described to you. And we're solving for G mu Q, which is a quantum correction. So by applying the procedures that I've described to you in words, we get the corrections to the outside of the star, which is given by alpha plus beta plus 3 gamma. So those are the local terms. You notice that those are the coefficient of the non-local term. You notice that the local terms do not contribute. And we have integration constants C1 and C2 that can be set to 0. So if you look carefully at these terms, you'll see that they will combine to give you a correction that goes as R to the minus 3 and R to the minus 5. And what is interesting is that this coefficient, or the coefficient of this term is proportional to G Newton squared times the mass times the radius to the minus 3. So that means you see that the quantum gravitational correction is proportional to the density of the source that we have picked. So if we have two source objects that have the same mass, but different densities, they will give rise to different metric perturbations. So let's show this explicitly. We're going to take two nested, so one inside the other, dust balls with densities ρ1 equals ρ01, theta Ri, so R1 minus R. And we do the same thing for the second configuration. And we want the total mass to, well, the total masses are given by, so M1 and M2 are given by integrals over these densities. We're going to pick R1 to be smaller than Rs, R2 to be Rs, and the total mass to sum up to M. So basically, we're building two stars. One that we've seen before, so that's the one with mass M and mass Rs, outer radius Rs. And we're going to compare it to two nested dust balls that have total mass M and the same outer radius Rs. So you can convince very quickly that solution in GR exists. So it's basically in the region where R is within R2 to infinity, the metric is the exterior Schwarzschild radius, sitting in with the mass M. And in the region 0 to R1, so that's the most inner one, the metric is the interior one, so the interior Schwarzschild solution. with radius r1 and mass m1 plus m2 times the ratio of r1 to r2 to the cube. And then again outside, so sorry, for r1 to r2, the metric is the interior Schwarzschild solution with radius r2 and mass m2. So we know the inside solution. So we can basically do the same calculation we had done before. So you know that in GR, in classical GR, an external observer will not be able to tell the difference between a star with radius rs and mass m from the star that has the two components with the same external radius and the same total mass. So there's no way to gravitationally differentiate these two objects. So what we find at the quantum, so that the quantum gravitational corrections are different for the two matter distribution here, and we thus have a memory effect of what went into the star. So again, this is the equation I was showing you earlier, and so I adjusted to the situation where we have the two layers. We find that there's a correction that goes as r1 cube and one as r2 cube, and the masses of the two different parts of the stars are here. So we see that this is a different correction to the one that we had for the star with a single layer, basically. So again, classically, the metric doesn't distinguish between the two situations. But for the one layer star here, we found that the correction goes as LP squared over R, G, NM over R. And that's the bit that is interesting. It's 3RS squared over 5R. So here LP is the Planck length. And for the two layer star, you find that instead of having the 3RS squared here, you get 3 times M1 R1 squared plus M2 RS squared over 5MR squared. So we see that the coefficient of 1 over R to the fifth is dependent on the internal composition. And that for that reason, the quantum gravitational corrections are different for the two stars. So we've shown that so the two layer stars has a quantum correction that differs from the single layered one. And we could easily generalize this to a star that has N and M layer stars as long as N equal M. And again, we can distinguish, or they can be distinguished by an outside observer because the quantum corrections are different for the two objects. So basically, we have a quantum memory effect, and you can think of this as hairy stars. So at the moment, we had a static situation, but you can restore time dependence by making RS time dependent. In that case, so basically, you think of yourself as being a distant observer as much larger at great distances from the radius of the star. And you expand the correction to the metric, and you find that the R to the minus 5 dependence remains during the totality of the collapse. So basically, at some point, RS will reach the 2GM limit, and you would form a closed trap surface. And that's what we, in that sense, we can extend these results to black holes. So basically, a distant observer could, in principle, measure the coefficient of the R minus 5 correction to the metric, and we would be able to disentangle, basically, or we don't have a memory of what went into the black hole formation. We could disentangle between the star with one layer or two layers. So we would be able to differentiate between black holes that were formed by different matter distributions. And in that sense, we see that quantum gravity produces a new kind of hair for black holes. So that was a specific example. So we're going to try to go into some more generic statement, and I'm going to mix a link to this discussion that Roberto was having on the quantum state of gravitons. So think of a compact source, which is an energy eigenstate with eigenvalue E. The graviton state that we'll call psi G of E is exactly analogous to the quantum state of the U1 vector field. So that's the Coulomb potential that will be created by charge Q. And you know that for the U1, that's what you obtain for the coherent state, where the B's here are creation operators, so a linear combination of creation operators of the non-propagating, so that it's a temporal and longitudinal, depending on the gauge, modes of the photon. So for the case of gravity, you would replace the charge by the energy value of the source state, and the coherent state modes are the temporal and the longitudinal graviton modes. So basically, both in the case of gauge theories and gravity, the asymptotic state would be fixed by the Gauss law via constraint quantization. So there's a direct connection also between the U1 and the gravitational field if you use the double copy relationship that is becoming very popular these days. So let's now go back to the case of gravity. So we've got psi g of E. So it depends on the energy. So each distinct energy eigenstate of the compact source has a different graviton quantum state, psi g of E. And if you think of a semi-classical matter configuration, that is basically a superposition of energy eigenstates with support that are concentrated in this narrow band of energies, we can write psi as a sum over n Cn psi n. So that here the psi n are the energy eigenstates with eigenvalues En. We get a gravity state that is a superposition state. So it's the sum over n Cn psi n of En. So in the case of gravity, sorry, of the case of QED rather, the long wavelength photon, as you know, coupled to the total charge of the composite object. In the case of gravity, the long wavelength gravitons coupled to the energy eigenvalues of the compact object. So basically, the semi-classical compact sources that are produced by external graviton states are complex superposition given by psi g. And basically, the star example that we discussed before is a concrete example of this general quantum state of the graviton. So how am I doing time-wise? I've got another 10 minutes, I believe, so that should be good. So we can then use this to think about black hole radiation and evaporation.
It's 8 minutes. Okay.
Sorry, excuse me?
You have 8 minutes.
8 minutes, thanks a lot. That should be fine. So to make our life a little bit easier, we're going to assume that black holes emit one quantum at a time. So we're going to take fixed intervals, for example. So in the end, we would have a final state with n quanta of radiations, R1, R2, R3, and so on up to Rn. So by Ri, we think of basically all the quantum numbers that are, so that would be the energy delta I, the momentum pi, the spin Si, and the charge Qi. So basically, this is a shorthand notation, Ri. So R1 is a shorthand notation for delta 1, P1, S1, Q1, and so on. So we can define the final radiation state by giving the values of R1, R2, and so on, R to Rn. Then we're going to call alpha of E and Ri the amplitude for the emission of a quantum Ri. So again, that's this collection of quantum numbers from the exterior metric state psi g of E. Now, obviously, at leading order, this is just the semi-classical Hawking amplitude for a black hole of mass E. But we will get some corrections to this amplitude. So in the leading approximation, again, you would expect to have the Hawking result, which is thermal emission. But the subleading order, you would get corrections that would grow as S minus K for perturbative corrections, or exponential minus S for non-perturbative one. And S, again, would be entropy of the black hole. So you would have additional dependence on E and Ri appearing at the quantum level. And basically, this is a consequence of the quantum hair we just discussed. So the fact that these corrections depend on the internal state of the black hole is possible because there's this quantum hair. So if you go back in the literature of the black hole information paradox, and in particular, a very nice review by Raju from last year, you will find, or people have shown, that even tiny, so those are tiny corrections, but even tiny corrections of this type can purify a maximally mixed Hawking state. So that means you can perturb the radiation density matrix rho such that the trace of rho squared is 1. And again, because the dimensionality of the Hilbert space, so it's of order exponential s, is so large, this will end up being a pure state. And that's some very nice result. Again, Raju has reported on this very nicely last year in a beautiful review on the topic. So let's think about the unitary black hole evolution then. So we take a black hole, it emits the first radiation R1, it evolves into an exterior state given by the following. So you go from the sum of n, Cn, g of n, to a sum n, sum of R1, C1, the amplitude we were just discussing, g, which is basically the metric, exterior metric that depends on En minus delta 1, R1. And the next emission, you will have C1, so you sum of R1, R2, C1, the first amplitude we had. Then we have the amplitude alpha of En minus delta 1, comma R2, and then G of En minus delta 1 minus delta 2, R1, R2. And finally, we obtain a sum of n, sum of R1, R2, and so on, up to Rn, Cn, these amplitudes that I've described to you, and notice that the geometry has disappeared because the black hole has evaporated. So that's the final radiation state. So basically, at this stage, the black hole is gone. There's no horizon, and space-time is approximately flat. And what you can see is that the final radiation state is a complex superposition which depends linearly on the initial black hole states. And under time reversal, the radiation state would evolve back to the original black hole quantum state. So basically, what I think I'm good in time, what I've shown to you today is that we can use effective field theory methods to do calculations of quantum gravity. We can apply that to calculate corrections to objects such as stars and black holes. And there's a sensitivity, though these corrections are sensitive to the inside of these objects. So that's a new kind of quantum hair. So from there, we went to a generic expression from the quantum states of the graviton field. And we've used this to discuss the evaporation of black holes and basically to argue that it's a unitary process. Thanks for the attention.
Thank you very much, Xavier. Okay. We have a question from Gia Dvali.
Yeah, thanks. Can you hear me? Yeah, so this non-local action that you presented is a pretty subtle thing. Actually, we don't know how to work with it.
Well, I did agree with that statement. I'm sorry, we know very well.
Let me finish the comment and then. So it's on its own, it's a highly subtle quantum field theory issue. We don't know whether it's complete. Even we don't know how to work with it. Sometimes we try to truncate as you do there, and then it doesn't make any sense because they are unphysical poles. And so what worries me is that you are taking this theory, sort of a theory, because we don't know how to work with it, and then you are truncate, and then you truncate, and then you declare that the beginning of your talk that this is just a straightforward QFT issue, and then you apply as if nothing is wrong with this unphysical poles and stuff, and then you claim that you can derive some quantum pair and make predictions, and I find this completely unjustified.
Well, what I find unjustified is your comments. You should just read the work of Bavinsky and Viloskovich from the 80s.
No, don't.
This is very well understood. I mean, we're having this discussion every time.
Don't send me to some other work. Hypothetical.
We're having the same discussion every time.
When I'm asking questions about your talk.
These poles are not an issue. It's a classical field theory. Show that there's a problem with these poles, and we'll talk again.
No, that's
it's very well understood.
No,
the interpretation is justified because we're doing perturbation theory.
No, sure. Of course, you can keep saying that. I understand because you gave a talk. Obviously, you're not going to say, sure, I mean, agree with me. I understand that. But I'm just making the statement.
You can't dismiss the work of
because there is
people like this without providing arguments. If you don't understand it, learn it. I'm sorry.
No, yeah, sure. I mean, obviously, I'm not seeking agreement from you. I mean, I'm not asking. I'm making this comment that I assume that you necessarily agree, but I'm just saying I see simply a conceptual, a huge conceptual gap, or problematic gap, because
yeah, this is simple.
Every step,
you know, we teach that to
is
every
like you are
nowadays.
No, I understand that you don't agree. I mean, that's fine. It's okay that we disagree, but that's my point. My problem is that the most interesting thing about gravity is that every time you try to sort of slightly modify the stuff, usually it doesn't work because it gives us some negative norm states, ghosts, and stuff like this. And this is great because that's precisely the way theory tells us that it's extremely constraining. And if we start arbitrarily truncating these non-local actions and treating the poles that do not make any sense because they're ghost poles as if they are normal particles, we're not going to get anywhere.
Again, I think you're
this
missing
is not
the
a
point.
prediction.
So
it's
a classical field theory, so there's no issue with the equation mark ghost.
Okay,
so,
already
and
that
truncation
statement
is no
shows,
other different. When you calculate an effective action in gauge theories,
so
are you worried about limiting yourself to one loop?
No, that state already the statement that you are saying
theory,
that it's okay to have ghosts in classical theory, already that statement is problematic. So I don't know how to proceed because we should, you see, in order to discuss, we have to discuss within the framework. So I'm ready to discuss within quantum field theory framework because that's what you said. But in the discussion, implicitly you are going out of the framework because you're saying it's okay to have ghost pole if I'm in classical theory, and that's, I'm sorry, but that's not true. I mean,
proof there's an instability in the specific framework, and we'll talk again.
Okay, that's that was my comment. So I mean, we can. I mean, I'll be happy to discuss in more details. But I think this is a huge problem because very often the theories that in reality they are not even theories because we don't know how to work with them. They are presented as if they are some well-defined
predictions. There's a problem if you can identify an instability.
Yeah, sorry to take more time.
So
no, we can continue. No problem. I mean, I'm sorry to be critical, but okay, sometimes you have to be critical because when I see something obviously wrong, I have to say something.
Well, again, this is not obviously wrong. I just think you don't get it.
No, sure, we can discuss. I gave you my argument, so yeah.
Okay.
Sorry. Oh, thanks.
I don't know, Javier, if you want to make some more comment.
No, I think again, this is if you make the effort to look in the details, this it's a very well established framework that goes back again to the 80s. And there's a lot of myth about the question of ghosts. I think the problem of ghosts is when you start to quantize them, that's when you get into troubles. But here the metric is a purely classical one. And again, until somebody shows me an instability within that framework, I won't change my point of view that this is a perfectly valid and acceptable way to do calculations in quantum gravity.
Is there any other question, either from Zoom or here from our local audience? If not, since we are a bit late, maybe we can move to our next speaker. And
Excellent.
Again, thank you very much. So our next speaker is Luca Smaldone, who is here in Covilha. Okay. This is changing.
Okay.
Okay, please, you can start.
Okay, thank you very much. Can you hear me? Yes. Oh, Hope it's okay. Okay, thank you to the organizers for this kind invitation. Very happy about this. I present this work I did in collaboration with Giovanni Accoglio and Alfredo Iorio. And that's the outline of the talk. First of all, we'll review some known stuff, very known stuff about black hole evaporation and thermofield dynamics. And then I went into more in the core of this talk, speaking about some Hilbert space of quantum gravity, the consequence of Bekenstein bound on it, and the concept of excellence we introduced. And then I will discuss about the exonic level. I will explain what I mean of this talk, and trying to argue that Bekenstein bound can be viewed as a consequence of this scheme. Okay, let us start. First of all, a couple of words about thermofield dynamics. What is thermofield dynamics? It's a formulation, a real-time formulation of quantum field theory at finite temperature, which was introduced by Umezawa and Takahashi in 1975. And the basic idea is the following one. If you want to compute a thermal average of some observable, in quantum theory, you typically compute the trace of A times rho, where rho is the density operator. But let us consider, for example, the case of canonical ensemble. The idea of Umezawa and Takahashi was, okay, is it possible to find some state, which is called thermofield vacuum or thermal state, so that the thermal average is computed as the vacuum expectation value of the operator? And the answer is yes, but this cannot be computed inside the original Hilbert space, but lives in a tensor product Hilbert space where we have performed doubling of the degrees of freedom. You see, n is our energy eigenstates, and tilde are the double degrees of freedom. This operation nowadays is quite well known in quantum information community, called purification usually. And interesting point is that the thermofield vacuum can be written in this form, where one can introduce this S, which is called the entropy operator, which is really the operator corresponding to entropy observable, and which takes into account thermodynamic entropy for sure, but even its vacuum expectation value gives the entanglement entropy, quantifies the entanglement entropy of the original modes and their double, the tilde modes, which, as you can see here more explicitly, are in an entangled state. Okay, what about black holes? Let us consider a simple example of sparse black hole, and then we take metric close to the horizon. This is very, very standard. Then we concentrate on the interesting part, which is the Rindler part, and we goes to imaginary time. And what we have is a Euclidean metric in 2 dimensions written in polar coordinates. So let's say the Minkowski, Euclidean Minkowski metric. And then now we want to do quantum field theory on such carved background, and we can do it, for example, in Schrodinger representation, and then a Hilbert space will be defined as a space of wave functional configurations, wave functionals on the field configurations, and Minkowski space can be written as a tensor product of left wedge and right wedge Hilbert spaces. And then if you compute the vacuum, the Minkowski vacuum, you can do it by standard functional integral techniques. And then you go back to real time, you find that the form of Rindler vacuum, of the Minkowski vacuum is a thermofield, is the one of a thermofield vacuum, exactly the thermofield state of introduced by Umezawa and Takahashi, where the temperature is 2 pi. Now, if you consider the black hole case and notice that difference on time parameter between Rindler and black hole here is the surface gravity K, you find that also the our talk in vacuum can be written in this way, but the temperature now is K over 2 pi. And this is clearly Hawking radiation, and from this you can deduce, you can also compute Bekenstein-Hawking entropy, which is proportional to the area. So once you recognize this was done for first time by Israel and in a more rigorous way than what I present here, you can recognize that you can use all the entire machinery of thermofield dynamics to study a quantum field theory on black hole space-time. So there is strict connection. In particular, you can calculate left-right entanglement entropy by means of the entropy operator. And so, just a remark, everyone knows here, I think, but clearly black hole evaporation we introduced here poses a problem, which is the information loss paradox, because you can start in a pure state with your system in a pure state, and then this evolves in a mixed thermal state. This in quantum field theory and Carver space-time description. And in principle, this seems to be a problem. There are many proposals. We have seen something also before. And Page, in a very famous paper, studied this problem, assuming that black hole radiation system is described by a pure state, and then he computed the entanglement entropy, and he found a completely unitary evolution and a complete recovery of the information. This is the most Page graph. Okay, this was the very introductive part. Let's see. Also, another fact is quite known is the Bekenstein bound, which is Bekenstein conjecture that every system with energy E and enclosed in a region with a radius R has an entropy bounded from above by such expression you can see here. And then if you consider also that in general relativity you must have such condition, otherwise you on radius and the energy, otherwise you have collapse into black hole, then you can deduce as a consequence of Bekenstein bound this holographic bound. So the entropy of every system is bounded from above from the black hole entropy, and so this is clearly both Bekenstein and holographic bound are saturated by a black hole. So what's the consequence of this? The consequence is the following: while in standard quantum field theory without gravity, in principle you have no. You can also think that you can have an infinite entanglement entropy, for example, between a system inside some region and outside. The region, this is so infinite dimensional Hilbert space, because infinite degrees of freedom. In when gravity is involved, only a finite number of modes can be excited inside some certain region, because if you excite too much energy inside a certain region of space, then this will, at a certain point we will have a collapse of the black hole. Let us remember the condition we've seen before. And then if you continue to excite quanta, we're bringing some energy, then what you have, you are just increasing the black hole at certain point. Radius of black hole will go over the original region, and so this, I would say, heuristic argument, but there are many similar, leads to conjecture, at least as consequence, that the dimension of every local quantum system has a finite number of degrees of freedom, so it's described by finite dimensional Hilbert space. Okay, we are not saying that the Hilbert space of the universe is finite dimensional, but it can be ultimately factorized in tensor products of finite dimensional Hilbert space. Okay. This was proposed by various authors, by Carroll and collaborators, by Toft and others. And the proposal, then one can notice that the equality holds for a black hole, where you have the saturation, and you can ask what are such fine number of degrees of freedom. Clearly, this should take into account for both for everything. For at a quantum gravity level, you should take into account both space-time and matter modes, so field and geometry. And the proposal was that such degrees of freedom are some more fundamental degrees of freedom. They're more fundamental than both matter and space-time, which are emergent concepts, and were called exons. And that's okay. That's the basic idea, which can seem a bit abstract, but as a quite immediate kind of consequences. For example, let us consider such exon living also in such finite dimensional Hilbert space H, and then take the projector of over, I would say, geometric modes and matter modes of such exons. Then you assume, let us assume, let us call the number of subspaces NT, the number of size spaces which correspond to a given macroscopic configuration of field over curved space-time. So each one of these subspaces can be factorized in a geometric field part, and so ultimately the Hilbert spaces, the Hilbert space of exon can be written in this form. It's factorized in terms of is not exactly factorized in terms of fields and geometry modes, but is written in this form. And so the idea which emerged from this is that although you can have, you expect unitary evolution at level of exons, and we will see later these facts, in principle, there are many configurations on exonic Hilbert space which correspond to a given macroscopic configuration of field over a curved space-time, which is everything we know. Essentially, all other things are conjectures. Other quantum gravity things are conjectures. And so, during evolution of a system, for example, black hole evaporation, these degrees of freedom can reshuffle, can rearrange, but many, for example, we can have many geometry configuration corresponding to a given field configuration. So, and so during the evolution, these field and geometry modes get entangled with each other, and you can compute in the spirit of page curve I showed before the entanglement entropy of field and geometry, and that's and you can do for various numbers of NT, or where is the okay, yes, yeah, I'm showing here for various combination of PI, QI, so that's their product corresponds to the dimension of TI. So you have many possibilities, and this is the origin of such entanglement. And if you study the entanglement entropy of field and geometric modes in as function of mass of black hole, what you find is a residual entropy at the end. So you have an effective loss once you introduce the concept of matter and geometry, even at quantum level. I would say in this moment, you have an effective loss of information, which is not fundamental, because we do not expect at axonic, I will say, at a fundamental level, but it's a natural consequence of this, because we have no access to all at the fundamental level, and so now we can try to reverse the logic, and we use what we have learned till now and try to build I would say, a toy model of fundamental dynamics for black hole evaporation. And first of all, we have to assume that our system has a finite number of quantum levels available. This is corresponds to locality, to the local quantum region, the local part of the sentence. And this because here clearly, because we are saying that space-time and geometry are emergent concepts, we cannot use geometric notions or finiteness of region or something like that. So we assume finiteness of quantum levels. Moreover, we take such accents, fermions, so they have to respect Pauli principle, and so you can have a maximum one mode for each of these quantum levels. And before black hole evaporation, you have that all accents are excited inside the black hole, so saturating the duration we have seen before. And the evaporation, the number of such accents decrease inside the black hole. You say, okay, but you are talking about inside and outside. What do you mean? What we mean here, without, and that's why this is toy model, why specifying how it works precisely, is that during the black hole evaporation, some of these accents interact and they form space-time and matter, as we mean, substantially. And when they form space-time and matter are out of black hole. That's an intrinsic notion that we have of inside or outside. So one which interacts to form emergent modes, and the one which are in their normal state. So then we use a second quantized language, and we call A and B, respectively the environment and the black hole modes, in the sense I was saying before. And these are our boundary conditions. So our initial state would be this one, and our final state would be this one. Which kind of model can fit this all this statement? Personally speaking, the only model I found that can fit all this statement is model of this type in a second quantized language. If you, as we showed in the paper, here you can find the reference to the paper. As we show in the paper, if you try to relax a bit this model to generalize, you always go in contrast with one of our assumptions, actually. Here, sigma is a parameter and is an evolution parameter, and we will comment more on that in a couple of slides. Moreover, we introduce entropy operator in analogy with thermofield dynamics that I showed before. And if we take the expectation value on this state of entropy operator, what you get is exactly the von Neumann entropy of the states. In the paper, we compare the von Neumann entropy, and you can find that this is the same. And this is in principle quite surprising, because we are not putting thermofield dynamics anywhere. So, and we will understand the reason of this in the following. And that's the von Neumann entropy of the system, which is quite normal entropy for fermionic system, say, but in this sense, okay, with our idea in mind, this can be viewed as the page curve, essentially, is the entanglement entropy of between environment and black hole in our case. Okay, this reaches maximum entropy when reaches the maximum entropy, which is n log 2. And the dimension of Hilbert space where this state lives is related in this usual way to the maximum entropy of the system. But this we computed substantially from. And what we can say, this maximal entropy is reached during when the evaporation is at the half. We can say that because, as we will see in a slide, we have no definite number of exon inside or outside at each stage. This means that you have half probability that the modes are inside, half probability that are outside. So you need the maximum amount of information in order to describe the model. And so clearly this, how big is it? It depends on how big we expect it would be strictly related. How big is it the black hole? It was the black hole at the initial stage of the operation, and so it should be a function of mass, angular momentum, and charge, clearly, which are still a concept which should emerge at a certain stage. But if you want to stay in contact with the semi-classical consideration, then we introduce the number operators in this way, and we take the expectation value of such number operators, and these are the results. And you see, I anticipated I will comment on sigma, and sigma can be interpreted in terms in the range we are considering. This relation can be inverted, and sigma can be viewed as a discrete parameter which counts the average amounts of fermions which are inside or outside. And the fluctuations give us a measure of the entanglement. This is in accord with, as you can see, is evident, but this is an accord with general remarks on variances as measurements of the entanglement, which was proposed in this paper, aside here. And so substantially now we want to introduce something which is can be viewed as black hole entropy, not the entanglement entropy or environment entropy in this context, and we want to compare everything. And in order to do this, we decompose the dimension of our Hilbert space in this way, using the fact that the sum is fixed, the sum of number of such modules. For example, 2, 2, and 2 is M is the dimension of a Hilbert space that will have a black hole with N2 available states in this picture, for example. So we can view, we can think in this moment, in this mode, that at each stage of operation, the number of modes, of exon modes inside black hole decreases, and that because of entanglement, you have fluctuations, so you cannot really decompose as a tensor products the Hilbert space of your black hole. But this is a would-be dimension of a Hilbert space, and it's for a smaller black hole, and so its logarithm is a natural definition for black hole entropy in this context, and so logarithm of n would be defined as environment entropy. And what we get is this one, and you find that S max, which is the maximum entanglement entropy, it's the maximum entropy available to the system, both clearly from black hole and for environment. Take into account that environment here, it means both geometry and so you are, when black hole evaporates, you create more space out of black hole in this sense, and more radiation matter. That's the basic idea, and that's in a sense formulation Bekenstein bound, so that if you have fermionic action, you have maximum entropy available to your system, and and both the black hole modes, but in particular also the radiation and the matter and the geometry modes should respect such bounds, should have an entropy which is lower than the maximum entropy available to the system. And then now we want to understand why description of this system is so close to thermofield dynamics, which would, okay. And in order to do this, we performed such canonical transformation. This is, you can check this canonical transformation, but it's very simple, but it's really non-trivial because it's not connected to the identity. So you cannot be written as unitary transformation. But still, because it's quite simple, you can find a vacuum state for new in the new representations, which is annihilated by the new annihilation operator here. And in case of radiation, it corresponds to the 0-1 vacuum, but in case of black hole, corresponds to a completely filled black hole. If you do this, you find that our state can be written as a thermofield-like state. I don't say it's really thermofield state because this is you have no thermodynamic description here. The modes are k-independent. For example, you have no momentum dependence. So, as also Gia Dvali said before, you have you expect you have a real thermodynamic description only when you go to infinite number. You take the effective description of a system with an infinite number of degrees of freedom. But in the case of a finite number of degrees of freedom, this is not real thermal. But the fact that you get a completely independent way, you get some thermofield-like state, it's quite remarkable. And it's connected in a sense with black hole. So you can also write the entropy operators before. Now to get in touch with semi-classical description, I would say, or just to trying to do a prediction, because clearly in physics we have to do a model, but we have also to predict something. We try to compare our quantities. We take really seriously what we have said, for example, that this decreasing curve is really Bekenstein-Hawking entropy of black hole. If you do this, you can, for example, compute the elementary cell to square Planck length ratio for such system, and for black hole, which is a parameter which is not determined a priori. There are various words, and what we have in this case this is 4 times log 2. This is in accord with general consideration, for example, in this old paper, where it was deduced that such parameters should be of the type 4 times log k, where k is an integer. So it's good. It's in a good agreement with this general prediction. And then clearly the number of our cells should be given proportional to the mass square of the black hole. And also this is something that probably is found also in quite different Dvali description, but we have similar relation between n and n squared. So in conclusion, Bekenstein bound seems to impose the Hilbert space of every local quantum system. It's a finite dimension presence of gravity. And so this Hilbert space should describe all modes, geometric fields, and so we can think that it describes some more fundamental modes, which are neither geometry or fields, and that concept of geometry and fields are emergent concepts. And when you do this, you find some entanglement entropy, non-trivial entanglement entropy between geometric and field modes. And you reversing the point of view, you can start from description in terms of such fundamental mode, assuming there are fermions, and you can find there is maximum entropy which is available both for black holes and matter and geometry in your system. And this model, far from being completely abstract, tries, even if it is a toy model, it's tries to give also a prediction on the alpha I introduced before. And as perspective, clearly we have to describe how precisely this emergence of space-time and matter works in a quantitative and rigorous theory. And that's something we are doing now. It's also almost completed. And comparison with the other approaches, clearly to page carve and the connection to some more structured quantum gravities, say like strings and so on. And clearly, and also another interesting point we also already started developing is how emergent, how different phases of system can emerge from such finite degrees of freedom description, as also I heard before from Dvali. Clearly, typically one says you can have this inequivalent representation of commutation relation only in the case of an infinite number of degrees of freedom. This is not completely true, because it's still known that you can have inequivalent topological representation. In particular, we studied both points in a quantum field theory in this paper here. This topological inequivalent quantization in a quantum field theory, showing that the both type of inequivalent phases can coexist, and you can even have in a quantum field theory inequivalent phases even if you are putting regulators, so you have a finite number of degrees of freedom in that case. So there are other ways to avoid some.
There is a question from Gia.
Okay.
Yeah. Hi. I had a different question, but briefly, since you mentioned at the end, I don't think topological number is a contradiction with what I said, because actually, if you take a topological number, topological distinct, which parameterizes topologically distinct sectors, and you resolve it as a coherent state, you will discover that the occupation number in that coherent state is infinite. So the topological number translates as a pole in the occupation number density of certain modes. And so therefore, that's an interesting comment, by the way. So no, it's not an exception, actually.
No, it's not an exception. It's another aspect was not included in your comment, I would say. Just
no, sure.
This. And we studied in a precise quantitative way in the papers I cited here. This point, but I agree with you in principle.
Okay. No, yeah, that's so that's interesting. So my question was this. Okay, I should look at the details, but many of the formulas look pretty similar. I mean, identical to what we get in quantum n-portrait, because in quantum n-portrait we also get this n coupless modes. And the entropy counting and everything that follows from there it's very similar. But so you didn't comment about any similarity or parallel or difference. I mean, of course, in our case, we are not postulating them; we are deriving them. So we have a microscopic theory, and we see how these modes emerge. But once they emerge, the counting looks identical to what you presented. So I think that's worth to have that parallel in mind as a one possible fundamental theory of what you want. So certainly our theory gives the exactly same counting. So therefore, yeah.
Yeah, very good comment. In fact, when I did this, I didn't have in mind. I didn't even know. I studied later your works, and then I commented it after your comments before, and I found you're right in a sense.
Yeah,
so.
Thanks. Thank you.
Thank you.
Another question, either on Zoom or from the audience here? If not, let's thank you again. And, maybe we can have 5 minutes break and then we meet again for the discussion session. So see you in 5 minutes, basically at 5. No, sorry. Yeah, in 5 minutes. Thank you.
Philippe, are you around? Do you hear me?
Yes.
Actually, I'm just checking this because guys which are there in Covilha cannot enter and they claim that Zoom is not working. But if I now cut everyone here as a host, it will not be great.
Well, anyway, I can hear you. I can't see you, but...
I believe most people are connected. I believe this is just...
Yeah, I can also hear you.
Yes, this is what I believe.
Well, according to Zoom, it says there are 23 participants.
Yes, yes.
Now that means they must be live. They may be asleep, but they're live.
No, Zoom is alive. This I see. I'm wondering about all of that. I mean,
Well, I'm here. Gia just said he was here. Well, maybe they went for the. I mean, a lot of people went for the break, and they may have just left the Zoom on, and they'll come back in a few minutes. I don't see Luca at the moment. And also, I don't see the people in Portugal.
yeah, this is what I'm worried about.
So they said they cannot enter.
Oh, they're the ones that can't enter. Oh, okay.
I don't know. This is what I'm asking. That's what you said, right, Alexei?
Yes, yes. No, this is like, yes, these people who are in Portugal. You see, my problem is that I supposed to be in Portugal, but I could not because I got some family trouble and I had to go to my home in another town. But anyway, so I cannot really judge what is going on there. I will just give them a call, and if they reply, I will see whether we start a discussion session right now or maybe wait 2-3 extra minutes.
Yeah, Alexei, the people in Portugal don't have to come in through the communal setup. They can each one come in through their own Zoom.
No, this is what they claim. They claim that from their side, at the moment, no one laptop can connect. So they have some issue with the network, I guess.
Oh, okay.
Oh, okay.
Just a sec, I will ask what's going on, and if they will discuss whether we start discussion now, or maybe in a couple of minutes. Just a sec.
Mm-hmm.
Hi, Luca. So what's going on from? Okay, well, so Zoom is definitely alive, so don't worry about that. Zoom is alive. No, I don't mind to share, but I suggest that we wait a couple of minutes more before you set the connection, because I mean, otherwise you 10 people will be cut.
Alexei, are you talking to Luca on a cell phone?
Yeah, I'm talking to Luca, yeah.
Well, he can put Zoom on his cell phone.
Sorry, Luca, say it again.
He can come into Zoom on his cell phone.
Well, if EduROM is not working, I mean, Luca, at least
something's working if you're talking to him.
No, this I understand. Maybe you can try just your phone, just in case. Okay. Okay, I see. Well, this is okay. So, well, guys, try to connect somehow. I don't know how can I help you. No, but if Joy is there, Joy is the best guy who can help. But did you call him? Yes, I'm texting. That's what it is. Okay. Okay, so I suggest we will wait for, I don't know, maybe a couple of minutes, and if...
Well, Alexei, if there are 10 people there, I think we should wait for them to be connected.
Yes. No, I understood they got some connection cut in the university, and this is a problem.
Oh, okay.
And I'm not sure everyone is eager to have a phone connection, because most of them are roaming. I don't know for whom and how it costs.
Oh.
Yeah, let's wait a couple of minutes. Yeah.
Yeah, I think we can wait. Robert have written me one moment that he will join discussion a little bit later. I mean, Robert Brandenberger.
I'm actually here.
Ah, you're here. Okay. So actually, only these guys who come to Portugal, they're a little bit disconnected for some reason, which no one knows why.
But my cutoff time is 35. So I can only stay for 20 more minutes because there's a train that leaves.
I see. But in fact, most of the speakers are here, apart from, I believe, Luca Smaldone. Everyone is here because Luca is important.
I don't see Javier, and I don't see Roberto. Oh, there, Roberto's here, yes. But it's just Javier I don't see.
Here is online, not online in the sense he's supposed to participate online. So, I mean, it's up to him to connect or not. I mean, I can ping him a little bit.
I don't know if there's anyone else from this morning. Anupam?
No, Anupam will not, because Anupam, he informed me that he has some obligations, some department obligation. He just unfortunately cannot. Well, maybe he will join some other day.
Okay, and then there's Ivano. Is Ivano here? No?
So success. People in Portugal are connecting.
I see.
Hello, sorry. We managed to connect again. There was the connection failure.
Okay, guys, so you're back.
Yeah, we are all back.
Okay.
So no computer to connect, actually. Sorry. Just.
Welcome back.
Okay. So yeah, we can start with this with the discussion session with the speaker of both this morning and this afternoon. I remember there was a question from Philip, actually, it's already raised hand, that I think he wanted to ask to Gia. So please, Philip.
Yes.
You can start.
I had, first of all, Gia, thank you for your talk. I had quite a few questions. The first one is just a small one that was actually raised by Robert Brandenberger in the chat. And he asked you whether or not you had a horizon for your scale,
yeah,
your maximum, whatever it was called. But may I ask, do you have what the mathematicians call a minimal surface?
Yeah, actually, that's very interesting because the answer is yes.
Yes.
So the thing is that all these Saturons, they develop, of course, horizon again is well defined only in n going to infinity limit, because obviously otherwise it's subject to quantum fluctuations. But in n going to infinity limit, there is always a horizon for all those modes that can carry information. Of course, since if we are not in the theory of gravity, obviously you can introduce some completely outside particle which has nothing to do with this theory, and of course that particle will not see the Saturn, that's obvious. But since the information is encoded in Goldstone modes, for example in flavor of, for example in Gros-Nivier, this is encoded in flavor quantum numbers. So therefore, in the limit, in this double scaling limit, which is equivalent to semi-classical limit for gravity, there is an exact horizon for any information carrier. So any mode with flavor quantum numbers, no mode with flavor quantum numbers can take any information from the interior of a black hole to exterior. So I even have a movie for the other types of Saturons, this solitonic ones, with the collaborators. I even have a movie that is, you can even see how the horizon is there. I don't know if I can find it, but if I find it, I'll share the screen and I'll show you the horizon. So the answer is yes, there is horizon in that limit always.
Good. Okay, second question is a comment on whether the graviton could be a Goldstone boson. It's very interesting that in the 1960s, shortly after Nambu-Yono-Lacinio, Bjorkane wrote a paper which he looked at psi bar gamma mu psi squared, and in Hartford showed that psi bar gamma mu psi got an expectation value.
Right.
I would imagine that if you did the same thing for psi bar gamma mu gamma nu psi squared, you get a spin 2 Goldstone boson.
Right. That's right. That's a very interesting history. Absolutely, it's very nice that you're bringing this point. And indeed, this gives me a possibility not to create confusion, because indeed there was this idea whether we can understand graviton as a Goldstone at the fundamental level. In other words, this has nothing to do with black holes. It's simply if we can understand a spin 2 particle, massless spin 2 particle as a Goldstone boson of some broken symmetry. And so that's a very interesting program on its own. It has some well-known difficulties, as you know probably better than me. And so so of course, when I said that for a black hole the Goldstone is a graviton, I didn't mean graviton at the fundamental level being a Goldstone. I meant that the black hole excitation, the Poincare collective mode of gravitons, is what acts as a Poincare Goldstone for a black hole. So it's very important to keep in mind this distinction. Yes.
Yeah, but what I was showing was that there are models where Poincare invariance can be spontaneously broken.
Yeah, but that's everywhere. Right. The idea was, no, that's a beautiful idea, actually. It has it has certain well-known difficulties, as you know. The idea is really fundamentally, but of course, that's a fundamentally different idea. The idea is that whether we can have a situation when the Poincare symmetry is fundamentally spontaneously broken in the vacuum, and whether Goldstone could be some sort of whether graviton could be some sort of a Goldstone boson of that broken symmetry. By the way, one idea to realize that was along this brane world sort of idea to embed some kind of a brane in higher dimensions and the brane pullback to think of it as a composite graviton. You would have pullback an induced metric on the brane and stuff like this. Yeah. So yes, that's a different program. Of course, I'm not going into that. I'm assuming that at the level of my discussion, graviton itself is a fundamental elementary particle, right? Okay. But thanks for this question. This is very important.
Yeah. Now, I want to say one thing. I disagree with you on the Gross-Neveu model. I'll come to in a minute. But I do agree with you on the discussion of ghosts that we had with Xavier. So let me just say about the Goldstones. You're perfectly correct that in Gross-Neveu, if you look at the 1/n corrections, you don't lose the Goldstone boson mode because you don't change the Hilbert space. You stay in the same Hilbert space where you had the dynamical symmetry breaking. But the question that was raised by Coleman's theorem and was answered by Drell, Yankeelovich, and Weinstein back in the 1970s was they constructed a whole different configuration, which was spatially dependent, which had lower energy than the Gross-Neveu solution. And in their solution, there was no Goldstone boson.
How can it be? Look, Philip. The bound state has a translation mode, right? Look, it's very simple to understand. Bound state has a translation 0 mode because by simple reason that the bound state breaks translation invariance, and correspondingly, it doesn't matter where I place it, it has the same energy. Yeah. So there is a mode which corresponds to that degeneracy. And that mode, of course, is a mode I'm talking about. That's the mode which is a gapless mode because of breaking space translations and time translations. So there is a mode, obviously. How can it not be? Because it's if your vacuum is Poincare invariant and your state is not, there is always a mode which translates the state by corresponding generator. And you will get a degenerate state. So no, there is a Goldstone mode. Of course, what is important, and that I think I try to answer that. What is of course important is following that to strictly have gapless mode, we must be in infinite n limits. That's true for always. That's true for black hole. That's true for why? Because in finite n, Hilbert spaces are not exactly orthogonal, and also at finite n, wave packets they spread. That's another way to understand why a localized wave packet is not an energy. It's not an eigenstate of the Hamiltonian. Never, for finite n. So there is a slight spread. That is absolutely true. But there is always a mode that at infinite n becomes coupleless.
Yes, at infinite n, I agree.
Yeah, infinite n, of course. I'm working in large n. Always we are working in large n when we talk about entropy, large entropy, obviously.
Okay.
Okay.
I also wanted to comment, it's related to Roberto. Usually when we say that there's a state that an annihilation operator annihilates, we call it the vacuum. Yep. Because in most cases, it is the state of lowest energy. But that's not a theorem. There are field theories where the state that is annihilated by the annihilation operator is not the lowest energy. And I think what you were saying to me, and what I was really trying to argue with Gia, is that state in Gauss-Neveu is not, in fact, the vacuum, the one that the Bogoliubov transformed annihilator annihilates. It's not the vacuum. There's something lower. And I think what Roberto was trying to say in his model is that the naive fluctuation h mu nu annihilator that annihilates a vacuum, that state is not the vacuum.
No, not in my definition.
The vacuum is the state of lowest energy. It's not the no particle state.
No. Okay, that's a common definition, but in my book, the vacuum is a state with no excitations whatsoever. It's a different thing.
Well, could there be a state with lower energy than it?
No, because there's nothing.
Obviously.
How can there be something? Define energy.
So, okay.
Well, what's energy?
Well, I can always define a T mu nu, and I can always integrate T00.
Yeah, that's a classical concept again.
Yeah, that's the best I can do.
Yeah, exactly. So by vacuum, I mean something that doesn't contain, again, no gravity, no matter, because gravity comes along with matter.
No, I mean, I think I agree with Philip in this. So
it could be minimum energy in a sense,
because I think the point is the following: if you have a system, right, what we have is that we have Hilbert space, and this Hilbert space splits into different super selection sectors. Now, if you are in the ground state in a given super selection sector, that's a vacuum, and of course, in that ground state, that ground state will not evolve anywhere. If you take it's the eigenstate of the Hamiltonian within a given super selection sector, and it will not evolve. Now, the definition whether there are no excitations, that's not an invariant definition, because excitations can be defined with respect to different creation annihilation operators. So therefore, I fully agree that once you are in the vacuum, you can consistently define your creation annihilation operators in such a way that none of them is present. So then the two definitions agree. But what Philip says, that's a universal definition. I mean, if you are in the ground state for given super selection sector, that will be a vacuum because it cannot go anywhere. It's just
okay, I can agree on that.
Right? Yeah,
I can agree on that. But
okay, I did want to make a comment about ghosts. I agree with Gia, but let me do that later because other people have to say something too.
Actually, there is a question from Luca.
Yeah, no,
Luca, mute yourself.
Yes. You're right. Can you hear me?
Yes.
Okay. So, no, my comment was, first of all, to Gia Dvali that at certain point, you finally mentioned what I meant before, these zero energy modes due to the presence of an extended object, because which are due exactly to the fact that the position of the extended object the absolute position has no meaning substantially. And that's what I am seeing you have before, and that's what is which are the modes you can combine to define the quantum coordinates of the extended objects in the definition of Umezawa, Matsumoto, and Semenov. That's that I was mentioning before. But as far as I know, there are no proofs of or rigorous proofs in quantum field theory of existence, apart from the case of phonons, for example, or some very specific case of a presence of an Goldstone boson for spontaneous breaking of Poincaré or subgroups of Poincaré, I would say. So,
well, I gave that proof in my paper. I gave that proof in my paper in 2020 paper about on Saturons for a generic bound state, and I showed that there is a state that you can define that with the gap that goes to 0 when n goes to infinity. So the gap that scales as 1 over n, because of, in particular, because of breaking of Poincare symmetry. So yeah, I don't know if you, I don't know to which extent you take it as a proof. To me, it's a proof because I just showed that if you have this type of approximate eigenstate of the Hamiltonian, as I said in the discussion with Philip, for finite n, localized solitons are not exact eigenstates of Hamiltonian because the wave packet spread, but that's also true for a black hole and for any other object. But the spreading time is so enormous, it scales like n, and so we can forget about spreading, and up to 1 over n, these are gapless modes. Yeah, so again, I'm saying I'm always working in large n because, but I claim that there is no other framework to talk about entropy. I mean, we cannot talk about entropy of a state if it's just one particle. Sure, one particle can be.
Consideration was beyond entropy. It was a discussion about Goldstone theorem in general, I would say, because I could be interested in a more general case, I would say, than this.
Well, I mean, in quantum field theory, the quantum field theory localized objects are made out of quanta. So usually these are some kind of coherent states or some the localized objects are solitons or this kind of. So in quantum field theory, so what I have shown is that whenever you have such a state, there is always a mode with gap that goes to 0 in large n limit. So yeah, that, to me, that's fully sufficient for me because in nature you cannot have modes that are more gapless than 1 over n. That's not possible because wave packets spread. There is absolute lower bound on the gap of any localized object.
But what I want to say, apart that this, when I talked about topological defects, I didn't have in mind the solitons, which fourthly have to be defined at infinity. But I have in mind, for example, point defects or vortices, strings type of defects, and so on. And in that case, you can there are topological defects in a different sense. The condensation density is described of Goldstone boson, you're saying, is described in that case not by a function which diverges at infinity, but it is described by a function which has non-Spartian point. Okay.
Which is what? Which point?
Trivial cohomology group.
Which point? Sorry, could you repeat?
I mean, when you describe, I agree with you on the fact that topological defects in quantum theory should be described by condensate of Goldstone boson. I agree with you about this. And I agree with you that about solitons you cannot do, you can do only in the case of a finite number of degrees of freedom. That's for sure. But also, I would say only in the case of system and infinite spatial in infinite spatial extension, because solitons clearly are stable because of a condition at plus and minus infinity. That's
no, of course. If you're talking about stability, sure, yeah.
But the type of when you try to describe as a condensate the defects of type like point defects or strings or vortices in a superfluid and a superconductor and so on. And here, in that case, it's different because the condition, the density of Goldstone boson is described by a function which is not divergent at infinity necessarily, but it's not transformable because it's a non-Spartian. For example, if for a string is non-Spartian in all points of of the strings essentially. So you have a non-trivial commutator of second derivatives. In that case, it means
So in other words, it's good that you are bringing this analogy. In other words, what I meant is that. But by the way, this is a very interesting general question, right? So what the question that Cesar, I and our collaborators were asking at some point was, I have a topological defect, right? So topological soliton. I mean, how does topology translate in the language of constituent modes? Okay, can I, if I think of this topological soliton as some kind of coherent state,
yes,
where is the topological number hidden? And what we have shown is that topological number is hidden in the pole at k equals 0 in occupation number. So this means that topology, and exactly this matches the precisely point that topology has to do with infinite boundary conditions at infinity. So that's why this
that's for soliton. But it's interesting that you got these results apparently independently, but this kind of studies were already done also in the 70s by Umezawa and collaborators, Umezawa, Matsumoto, Takahashi. And
oh, you mean for topological objects?
Yes.
Like in relativistic field theory. I was not aware of that.
In relativistic or non-relativistic field theory. They also
non-relativistic, sure, because we have condensates in condensed matter and stuff like that.
Even for solitons. There are papers, for example, by Vitiello and some paper. Yeah, for sure, some paper by Giuseppe Vitiello.
Okay, so I will look it up. Yeah, I was not aware that anyone translated topological numbers.
I understand that you draw it independently, but I tell you, in the case of vortices, it's different kind of condition, and it's related to a non-trivial cohomology group. And okay,
I agree. Yeah.
I can show you. I can also send you my paper, and I would be curious if you can send me your work on this.
Sure, happily, yes.
Symmetry, because I'm interested about this.
Yes, absolutely, sure. Thank you.
And I had another comment about the story of the definition of vacuum. I understand it's very delicate. Because it depends what is your formation in a sense. If you are a mathematical physicist and you take the Berezin book, for example, beautiful Berezin method of second quantization, the vacuum is defined in context of a representation theory of canonical commutation relations, and in that case, the vacuum is defined as the no particle state.
I agree fully, but
in the case, but usually physicists define as the minimum energy state. There are, I think, for what I can say, I think there are advantages and disadvantages of both definition. For example, thanks to the case of time crystal, in the sense of Wilczek. And in case of time crystal Wilczek, you have spontaneous breaking of time translation symmetry. In that case, the vacuum, by definition, cannot be viewed as an eigenstate of the Hamiltonian. But what Wilczek correctly says is that you can end up in that configuration. And if you are in a system, as you were saying, with a finite number of degrees of freedom, probably you can be stuck in that configuration because you are stuck in that Hilbert space, stuck in the sense that this state cannot be changed by local operation, can be changed clearly if you have some external force which pump energy or something like that. But in that case, you are changing global boundary condition of the system. Otherwise,
well, okay, there is a subtlety there because I want to reiterate that Philip's definition is universal, and that always works. In other words, because once if you can clearly identify lowest energy state of your Hamiltonian within given superselection sector, that automatically will be a good vacuum also with respect to other definitions. Now, the converse, of course, is not true because, as you said absolutely correctly, so if I define vacuum with respect to certain quanta, this same vacuum with respect to other quanta may not be a vacuum. I mean, Bogoliubov transformation is the simplest example of that precisely when you have particle creation from the vacuum, precisely because of that. So these two are not inter-exclusive. But what I'm saying is that usually, of course, in nature, we never encounter infinite occupation number states. All the states that we have usually have finite occupation numbers. And that's why this notion of Goldstone theorem and vacua, these are approximate. In practice, they are always, in practice, when we encounter these systems, they are approximate.
Yeah, as you can see, I agree with you.
But in the hypothetical limit of infinite n, then Philip's definition is correct. So once you identify ground state, it simply cannot go anywhere. It's a ground state. It's a eigenstate of the Hamiltonian. It is bound to be a good vacuum.
No, but simply saying that sometimes you can have reason for defining the other way. For example, I mostly work during my short career on problem of describing neutrino mixing in quantum physics.
I fully agree. Absolutely.
In the case of the neutrino mixing description field theory, you can say that the mixing transformation of fields is a Bogoliubov transformation.
Yeah, it's sort of a Bogoliubov transformation. I mean, the simplest one.
It's more general, yes. It's not simple Bogoliubov transformation, but it's a canonical transformation.
Which, of course, it's a canonical.
Yeah, and so then you have to do a choice. Do you want state of minimum energy, or you want the state of zero flavor?
Exactly. That's precisely an example of the second definition when the vacuum is defined with respect to modes.
Exactly.
And so that's what happens. So absolutely.
What we choose, or with zero flavor, for example. In that case.
Right. Absolutely. If you define your vacuum as zero muon flavor or electron neutrino flavor, that will not be a vacuum for the other flavor.
Exactly.
Right,
So it depends on the physical situation, I would say.
Sure, I fully agree. Yes.
In fact, we formalize this problem by in that specific context by formulating some flavor energy uncertainty relation. So our flavor energy are incompatible observables, and then you have to make a choice substantially in that case. So it depends on the choice. Which vacuum definition do you want? In that case, you have duality, and you have also uncertainty relation.
No, I agree. Yeah, in that case, it's a matter of convenience. Yeah.
I think Philip, you had another question, right? You wanted to comment. You're muted.
Javier Calmet is no longer here because
he told me I had to leave, unfortunately.
He couldn't be here. Oh, okay. Because I was going to raise with him the same issue that Gia raised about ghosts. And what maybe someone can remind me, in deriving his effective field theory for gravity, was he already using quantum gravity to get there? Because the answer he gave to Gia was basically to say, no, this is a classical theory. So I don't know how he obtained it, other than by doing something with quantized gravity. And if he did do, then the quantum version of the theory that he's working with definitely has ghosts. Now, I'm not saying that's the end of the world, but I mean, the issue he's raising was whether or not he had to deal with ghosts at all. And he was sort of saying no, because this is classical. But if it's classical, then I didn't quite understand what it's got to do with quantum gravity to begin with. And if it's quantum mechanical, then yes, there is a ghost problem. Now, I mean, I've personally solved that ghost problem. I'll talk about it on Thursday, but that's not my concern here. My concern here is there a ghost problem or not in the work that Javier presented? That's my question.
Can I step in?
Sure.
No, there's no ghost problem the way I see it. It is an effective action that is meant to, can you hear me?
Yes, we can hear.
It's an effective action that is meant to hold in the weak field approximation for the gravitational field produced by a certain mass distribution. The corrections to the Einstein-Hilbert Lagrangian or Einstein-Hilbert action come from integrating one loop of standard model fields in the usual way It's a one-loop effective action. Again, it's meant to only be used to compute weak field corrections to the metric generated by a source. There's no, in order to say that you have ghost, you should include even higher order terms in curvature that we don't need, because those in our calculation would produce lower order corrections that we neglect.
Okay,
so I don't think there is a ghost problem.
Roberto, can I compliment Philip's, because I fully agree with Philip again. I mean, it's
Sure.
so can I compliment his, he formulated very nicely, precisely, because I don't understand your answer, because here is my very general problem, and it precisely goes with what Philip was saying. So look, you have a theory, okay?
Yeah.
So this theory you obtain somehow. Okay, you are saying I integrate one loop or two loops. I grant you that you come up with a theory. Now, if you tell me that that's a quantum theory of gravity.
No, it's not.
No, but he was talking about quantum gravity.
Oh, that's not the way I see it. No, it's an effective classical.
Okay, let's
theory.
go to classical. Okay, so now you're telling me here's the theory of gravity. Okay, you call it classical, but then I don't understand why you include one loop, because loops are quantum. But
yes.
Okay, I mean, you have some sort of hybrid. Okay, you do quantum computation and you obtain a theory. Okay, fine.
That's a minimal effective action, right? You
but
include quantum correction and you obtain an effective action that holds at the classical.
Yeah, but effective action doesn't have to be classical. Effective action can have a classical limit, but the action is quantum, because we are in quantum theory. It's suppressed by Planck scale. Right. Anyway, let's not argue about semantics. This is not.
Yeah, that's semantic.
Right. So you have a theory that you tell me this is a classical theory. Fine. Classical or quantum, I need to work with this theory. Now, this theory, so this is a huge challenge on its own, how to work with this theory. Why? Because when theory contains ghost faults, either classical or quantum, we need some very specific prescription. We have to go beyond the standard quantum field theory approach. So, so therefore, you cannot sit on two chairs, so to speak. You cannot, on one hand, tell me that you have a theory where you have ghost poles and you use these ghost poles to give predictions.
We didn't use the ghost poles in our calculation.
Why do you have deviations from gravity otherwise? I mean, I don't understand. Then why don't you forget high derivatives?
No.
Look, I think what Roberto is trying to say is that what Xavier did was he treated the gravitational field as a classical external field.
Yes.
Quantum loops of ordinary matter.
Yes.
And that induces higher derivative terms in the curvature.
Correct.
However, what Gia and I are saying is that when you quantize that theory,
we don't.
But you have to if you're talking about quantum gravity. At some point, you've got to quantize the theory.
Right. I fully agree.
I mean, otherwise, it's not relevant.
Right.
I mean, it may be relevant for some classical applications, but at the end, you've got to quantize that theory. And if ordinary fermion loops, for instance, generate higher curvature terms, then they will induce in the quantum theory issues that we call ghosts.
Okay.
Right.
And you can't get around that by saying, I'm not going to quantize the theory. I'm not going to quantize the gravity piece.
We have a comment from the audience. Maybe you can also.
Thank you.
Yeah, hello. I agree with you. Let me just put first a disclaimer that, of course, I don't know exactly what Xavier had in mind. It's a pity that he's not here. But just to summarize, there was also a question from Mannheim. Maybe I wanted to sort it out. So as I understand, Xavier took as the first classical action that he quantized, he took Einstein-Hilbert. Then effective field theory, this is effective action.
Yes.
I agree that this is with full quantum effects, but let's say we take it to the first loop level and to the level quadratic in curvature. Of course, you know that you can expand effective action, which is a quantum object. You can expand in these two different expansions. One is a loop expansion, another is curvature expansion. So we agreed that we reach this point, and when we have this action functional that Xavier wrote. Now, I think I understood that he took this action at face value, and now he declared this is a classical action. I want to study exact solution of. So now this is
corrections or exact solutions.
He got a classical action, and then he studies equations of motion.
Yes.
And now I think that for this business, actually for 1-point function, so like in true general relativity, we are not interested in 2-point functions. We are not interested in higher point functions either. So the problem of ghosts may not appear so evidently. I of course agree that when you have equations of motion in this not only higher derivative, but also non-local theory, there are some problems, but it doesn't make so evident that you really have to deal with ghosts. So here I agree with Roberto that yeah, the ghost effect was not there because we didn't, I mean, he didn't need to compute 2-point functions. If you recall what is
that's sorry, okay, so let me clarify. Yes, absolutely. Thanks very much for the
1-point function, and that's what he was doing because he wrote for us this, I think, complicated equations of motion with higher derivative terms, with non-local terms, and then he tries, okay, maybe this is when the devil sits, he tries to solve this equation in exactly.
Yes, but that's what I'm saying, that is inconsistent.
Of course, I said I'm not completely. I don't know whether Javier would agree with me or maybe not. But I also know that even in this classical exact solutions of this action that he declared to be classical, forget about quantization. Sorry, so even in there are some problems of the type that there are instabilities. So I know that the papers, for example, Ilian, Rhodes, Shapiro, and others, that they show that even if you take this classical action, you just study classical exact solutions, so not going to propagator, not studying the spectrum, but just classical exact solutions, you already see that there is a problem. You can phrase it like Ostrogradsky, but you can also say that there are some instabilities, and then okay, maybe his special framework of just studying black holes, maybe it hides them. I don't know, but generally.
Okay, let me try to.
Sorry. I mean, sorry. I mean, I understand what you are saying fully. But I mean, I don't agree that can be a consistent program, because look, I mean, there are people that are trying to make sense of theories with ghosts. I admire Philip, probably is one of them.
Yeah,
that's a different approach. Okay, so if you are telling me I want now to come up with some sort of prescription or some sort of understanding of quantum physics, certainly it has to go beyond standard field theory and want to make sense of ghosts. That's a separate program.
No, that's not what you're trying to do.
No, right. That's precisely what worries me. If you would tell me, yeah, this is what I want to do, there are people that are trying to do that, and I don't think that is so easy to make sense of ghosts, because otherwise we would not have textbooks.
No, they should not be there in the full theory. I agree.
So now, therefore, I don't see how a program in which you tell me, look, I do one loop computation, I derive some action. This has high derivatives. These are well known to contain ghost poles. This is not something new. This is well known. And now you're saying, okay, look, there is a way to treat this theory halfway. I treat it classically. Obviously, there will be interesting effects come from high derivatives, because this is a theory of high derivatives.
Yeah.
But then you say, okay, look, it's like a cherry picking. You want to get some predictions from high derivatives without worrying that the underlying physics is completely inconsistent. And physics cannot work like that. We cannot just.
Let me put this away. Suppose the consistent theory contains higher order terms than the ones we have kept.
Then you have to resum them and tell me how to work with them.
I can show you that those higher order terms would lead to smaller corrections to the metric in the 1/r expansion, which is the one I'm interested in. So why should I keep them?
Sure, but they come from poles which are ghost poles, and therefore they are not trustable.
You're scattering it. It will not be unitary.
It will not be unitary. These are small non-unitary corrections. You understand what you are trying to say? You are saying, look, I have a theory. I have poles that violate unitarity. Look, these corrections, non-unitary corrections, are small. Therefore, let me treat them as some sort of perturbation. But non-unitary correction is a disaster. It's not small. It doesn't matter how small it is. It's simply inconsistent. So my problem is, and this is everybody's problem, this is the problem of textbook problem, I'm not inventing it, that we cannot, on one hand, make predictions from small corrections coming from ghosts, and then on the other hand say that, okay, we are not taking responsibility for those ghosts. So that's my problem, okay?
Well, but you see the ghost in a regime which is not the one we use. So in
no,
that regime, the theory is going to be different.
It doesn't matter which regime you use. If ghost pole were not there, you would not get any correction because they go hand in hand. You cannot write a high dimensional theory truncated without a ghost pole. So they do not decouple. There is no consistent limit in which you don't have a ghost pole, but you still have corrections that are interesting.
Yeah, in a scattering process, you can release a large number of negative norm states.
Exactly, right, absolutely.
If you have any. I mean, the S matrix just collapses.
Absolutely, I fully agree with that. Yeah.
So you're claiming that all non-local corrections are unacceptable?
No, not all. No.
Which one are acceptable then?
Well, we're only claiming it so far for the one that Javier just presented.
Okay, those are completely unacceptable then.
No, I wouldn't say they were completely unacceptable. I mean, it's unacceptable to pretend that there's no problem.
Right, exactly.
Okay, but I'm not pretending that there's no problem.
The question of Roberto, probably the corrections which are higher order in curvature, like RQ, you know, that they will not influence the propagator on flat spacetime, so they will not really deal with the issue of ghosts. But in effective field theory, if you go to higher order, like cubic in curvature, you expect to generate them too. So, so I think with these corrections, Philip and Gia probably they could be.
But sure, I agree. But we don't base predictions on those things that we do not come from problematic poles. It's okay to say that I write down. So normally, how we operate. Of course, all of us we understand that if we compute high order loop corrections, there will be some high order corrections to Einstein action. We're not normally worried about those corrections. Why? Because we say at low energies, we use Einstein. Einstein is ghost-free, and therefore we trust predictions of that part of the theory. Now, the problem is if I want to sort of cherry pick, I say now, oh, no, I want to use these higher derivative terms to make some predictions, but I close my eyes on problems that they bring. And that's an inconsistency. That's what I'm saying. I cannot trust. In order for me to trust your predictions, I have to be sure that they come from the controllable corrections. And ghost corrections are not controllable. As Philip said, no matter how small, the S matrix collapses, for instance. So this is the problem.
Yeah, maybe I can state the issue slightly differently. Normally, starting with Einstein gravity, we're worried about renormalization.
Okay.
And we generate loops, but if you start doing matter loops rather than graviton loops, you generate terms which have negative signature.
Yes.
And so that makes the problem a lot worse. And that's the concern that Gia and I, in other words, the issue is no longer just renormalizability.
Exactly.
Now the issue becomes unitarity. And that was the concern. And the only thing we were saying was, Javier, you can't ignore it. We weren't saying that you have to come up with a solution.
No. On that, I would agree. What I'm saying is that if the theory has to be consistent, there must be higher order terms to make it fully consistent.
Well,
but those higher order terms, whatever they are in that expansion, they would not contribute.
Roberto, you're expressing an article of faith. You're not.
Right.
You're saying what you're saying is there better be higher order terms that take care of. Not saying that there are.
No, there better be.
There are theories that are sick and that remain sick no matter what you do.
But that would be Einstein theory is sick if what you're saying is true.
No, what I'm saying,
Einstein gravity plus matter is sick.
I'm going to make the statement a little bit more carefully. Okay. Radiative corrections generate higher derivative terms.
Yep.
If you have no solution to the ghost problem, those theories are sick, period. Now, what I have done in work with Carl Bender is precisely to find solutions to the ghost problem. It's not something that you can ignore. But nonetheless, the good news for all of you is that our solution allows second plus fourth to be both renormalizable and unitary. And so that's the result we published in PhysRev Letters a few years ago. But what Gia and I are trying to argue is, it's not enough to worry about renormalizability. You've got to worry about unitarity as well.
Yeah. Okay. So maybe we should use your action to compute our corrections then.
My theory.
Yeah.
Well, that's what I've been saying. The point here is that the whole ghost issue presupposed that you're supposed to use the Dirac norm and the overlap of a state with its Hermitian conjugate. And what Carl and I found in these high derivative theories is that the Hamiltonian is not Hermitian and that you shouldn't be using the Dirac norm. Rather, you should use what's called the PT theory norm, namely the overlap of a state with its PT conjugate. And that one turns out to be positive. So what we're really saying is, you have to do something with the dual space, not with the ket. The kets are what they were before, but the bras are no longer the Hermitian conjugates of the kets. They're the PT conjugates of the kets, or in more generality, the CPT conjugate of the ket. Okay. And that norm turns out to be positive definite.
In practical terms, can I phrase that in terms of corrected Einstein equations?
It's not you don't change the Einstein equations. What you're changing is the Hilbert space on which they act.
Okay, so can I phrase that in terms of semi-classical Einstein equations so I can compute corrections to the metric, or there are no corrections to the metric?
No, okay. The metric changes in higher order. The Hilbert space does not.
Okay.
Higher order
in what?
If I can maybe ask the question.
In interactions, in any interaction you want to introduce. It's basically what we've been saying for the last half hour, is first you've got to find the right Hilbert space.
Sorry,
before
Philip.
you can do anything.
Philip, I have a question here. So let's suppose we take quadratic gravity and we quantize it with the prescription that you used with Carl Bender. Okay?
Yes.
And now you know that we have a theory whose bare action is basically just Einstein plus curvature square term, r squared plus y squared, for instance. And you want to compute loop correction for this theory. Okay. You would or you want to couple this theory, for instance, with
let me be very careful. If you have second plus fourth, you have a massless graviton and you have a massive particle. Sure. And that massive particle is going to change what you call a gravitational interaction. Sure. It will be a renormalizable theory, it will be a unitary theory, but it will not have the standard content that you look for in Einstein gravity.
Oh,
and there will be corrections to the 1/r law, for instance. Now, the alternative is the one I work in, which is pure fourth. And then that problem doesn't arise. But as far as second plus fourth is concerned, the work that Carl and I have done allows it to be renormalizable and unitary. But its change is in the particle content, because higher derivatives means more modes than just in second order. That's the difference.
So my question was, if you do have a loop computations in your theory, would you generate this type of logarithm correction in the finite part of the effective action?
Yes. Yeah. What it really boils down to is the extra graviton, and you've got to follow the argument very carefully. The extra graviton appears with a minus sign, and that makes the theory renormalizable because it cuts down the ultraviolet divergences. But it looks like you've lost unitarity because of the minus sign. But then Carl and I show you how to reinterpret the theory by changing the the norm of the Hilbert space. And so now we have a Hilbert space where we have a 1 over k to the 4 propagator instead of a 1 over k squared. So now everything's nice and renormalizable. But at the same time, we don't have any problems with negative norm. And so, and that's the theory. But the price that you're paying in order to get that much better behaved propagator, 1 over k squared minus 1 over k squared plus m squared, is you've got an extra particle now, which you didn't have before, and which for the moment we've never seen. But on the other hand, that's not the end of the world, because we haven't seen a graviton either. So, but you will have some corrections, and the only thing that I will concede is that mass could be Planck scale. Nothing forces it to be light. So maybe there I'm prepared to agree with Gia. Higher order corrections can still be suppressed, but not non-unitary corrections. They can't be suppressed. Now, the difference is that when I work in the pure fourth order theory, I'm able to get rid of those extra particles. That's the only difference. And that's, I'll go through this on, having just given the talk, I'll give it again on Thursday.
So, I don't know if there are any comment questions from the audience here. Okay, I think it's a good time maybe to wrap up, and maybe we can thank all the speakers of today and for both talks and the discussion session.